Yeah, just attendees use the Q&A instead of the chat to ask questions.
Yes.
All right. Good luck, Chris. See ya.
All right. Yeah. So hello, everyone. Today, what we're going to be talking about is how do you do scientific machine learning with Julia's SciML ecosystem. So we've had a lot of recent talks all around. You can go on YouTube and you can see all the exciting stuff that we've done with scientific machine learning. But the purpose of this workshop is not for us to show you what we've done. It's to show you how to get started in doing scientific machine learning yourself, so you can start to do all sorts of exciting things and make airplanes fly with batteries and all these different things that we're showing can work when you start to augment these scientific models with machine learning elements. So first of all, what should you expect from this workshop? What we'll do is we'll go through what is scientific machine learning, because just to start, I think that most people still don't really know what scientific machine learning is. So we'll give an introduction and we'll go through a bunch of different examples of how that was done and what kinds of use cases people have found for scientific machine learning. And then what we'll go do is we'll go through the package ecosystem and really try to showcase how to utilize these tools in tandem to be able to solve these scientific machine learning problems. So how to do things like parameter inference on differential equation models, how do you add events to equations, add stochasticity, add delays, do Bayesian inference, right? So be able to get probabilistic estimates of your parameters instead of just a deterministic estimate. And so we'll be doing a lot of different activities like that to be able to demonstrate how you can incorporate data into the models that you're generating and then be able to generate new models with new data. This tutorial is meant to be raw. So it was meant to be live in some sense, where we get everyone live coding and we do a lot of one-on-ones. We've had to transition it to the online format, but I still want this to be doing some live coding. So we're going to be doing live coding. I'll be showing it on my screen. I'll be writing it in and running it. And so when I say we, I hope it means you as much as me, right? I want you to be following along. I want you to be looking at these tutorials. For the most part, what we'll be using as our tutorials for today are going to be the actual written tutorials of the given websites, right? Since we have enough information out there, we have a lot of tutorials, we have a lot of documentation, and so a lot of what this workshop will be doing is showing you around those resources, so that way you know where to go back to when you're going to do scientific machine learning on your own. So a lot of what we're going to be showing today is really just how do you learn to navigate the ecosystem? What are the different packages that you should make use of? How do you use the IDE correctly? And maybe as I'm live coding, also just how do you work with these error messages? How do you instrument the solvers, right? So you can, the whole thing is written fully in one language. It's a full Julia stack all the way down to, we have our own BLOS implementations and our own implementations of floating point exponents at this point, right? And so if you can instrument the whole thing all the way down, and so as I'm doing some live coding, I can show you how to be able to diagnose what's going on just by looking at any part of the entire ecosystem here and be able to see how these elements are coming together. So the first thing I want to do is tell you how you can help, right? So a lot of people think that the only way you can help an open source project is to contribute. And that is one major way to help, but it is not the only way to help. So for example, one nice thing that you can do is just star the repositories, right? Just showing that we have support is one of the ways to be able to, for us to be able to get more support in the future. And so if you star things that you like, maybe differential equations, diffeq flux, data-driven diffeq, all of these will be helpful for us in the near future. Not just the SciML packages, but also these other packages from the greater ecosystem, like flux.jl, zygote.jl, sparse-diff-tools.jl, everything in this entire Julia ecosystem that we're building on could always use more and more support. So one of the easiest things to do is to start the repositories. Another thing to do is just report any bug that you find, right? We don't know if you're having problems if you don't tell us. So please tell us any bugs that you find. Those bugs include error reports, and also those bugs include performance reports, right? Don't feel shy to be able to say, here's a code that I ran, and it's not running as fast as I would expect because it's X speed over here and it's Y speed in SciML, right? It's when we see those issues over thousands and thousands of these issues that we've been building up more and more performance, right? So if you really want to help us out, and especially in your domain, please share us whatever you can. If you can only share us a snippet that can go public, then please share that. If you want to keep something private, we can work on things privately. We can utilize all this information to build a larger test space and make sure that we're getting more performance in more domains. So please feel free to report bugs, error messages, and performance. Other things that you can do is just create other tools for the ecosystem. So create tutorials, write blog posts, right? They could just even be a quick blog post that says, here I trained a universal differential equation on this data and it seemed to work, and share the code that you have, right? All these kinds of things build up a whole atmosphere for other people to be able to learn, right? Because one learning exercise or one learning tutorial is never going to be the right one for everybody. And so if you share these materials around, everyone can, as a Google search, they can find the tutorial that works for them. Other things to do is share data and challenge problems. So today we'll be launching a new challenge problem, this magnetic navigation challenge problem. And with this, we'll be basically giving you data and a scientific model to be able to perform scientific machine learning. So we also have another challenge problem out there, the helicopter SciML problem. So these all come with, there's a first, a principal derivation of the physical model. The physical model is implemented in Julia, utilizing global optimizers. And then the SciML components are put on there to be able to find missing parts of the physics and be able to improve the model. You can take those from there, and you can utilize your own SciML ideas and be able to use this to be able to test out new ideas and get your own publications and get quickly to the state of the art by utilizing these already implemented, optimized implementations of the scientific models. So if you want to also help, you can also share more of these challenge problems. The more of these that exist in the ecosystem, the easier it'll be for new individuals to get into the community. The other thing to do is just help out in community chats, right? So people are asking questions all day. We have a very lively chat in the Julia Slack. If you don't know about the Julia Slack, check out slackinvite.julialang.org or the community tab of julialang.org. And so inside of this Slack, you can find, I think we're at over 500 people now, and there's a daily conversation going on, probably messages, sub-hourly, sub-minutely, just ongoing chat about different things people are doing with differential equations and different things that people are doing with neural networks related to differential equations. And so one way to help is just to join in the chat. And if you know something, just share what you know. If people ask questions, help them out. Or if you have questions, that's also a great place for you to go. The other thing that you can do is we'll be describing how there's this common interface that many different packages can work on. So if you want to develop an ODE solver, if you put it on the common interface, then all of these tools for scientific machine learning will automatically work with your ODE solver. And so please, if you're doing research in ODEs, make sure that you connect to this common interface and we'll be able to work with you. And the other thing, the very last thing is you can contribute to the SciML packages, right? So everything here that we're showing is open source. And so you can always support us by contributing back to this ecosystem. But I just really wanted to point out that this is not the only way to contribute to open source, right? Even something as simple as just tweeting out one of our repositories always helps. So we really enjoy it if you contribute to our packages, but there's many other things that you can do. And we thank all of the different groups that have previously helped with our SciML development, including ones such as our new sponsor to the Julia Lab, the Microsoft Studies in Pandemic Preparedness. And Simon Frost actually has some really nice repositories showing how to do epidemic modeling in Julia using a lot of our tools. So what is the outline for our workshop? Well, first we'll be going through an overview of scientific machine learning and SciML. So I'm going to make sure we're all on the same page and really understand the ways that these methods are being used and the ways that the methods might be able to be used in the future. So we're going to ask and answer the question, what is scientific machine learning and what makes the SciML ecosystem unique, right? So what are the tools that you have at your disposal to possibly solve some new problems? And then what we'll be doing after that is, we're going to be doing a quick bit of modeling and then go into our introduction to the challenge and learning problems. So we have a bunch of workshop exercises. A lot of them have answers, a lot of them don't have answers yet. And that's one nice place you can contribute if you want to give things a try. So all these workshop exercises, they have a lot of nice models like the Origo model, and you can use these to be able to get started with our differential equation solvers, get started with fitting neural stochastic differential equations, and all of these other problems. The helicopter SciML challenge problem will be introduced, and that one has a laboratory helicopter where we've gotten this data on electrical inputs to these rotaries and a bunch of physical measurements. And for that challenge problem, we have a full model, and you can utilize that to be able to do automated discovery of the missing physical elements. And we'll be launching this new challenge problem on how do you do navigation without GPS by utilizing the Earth's magnetic field. And then what we'll be doing after we go through modeling with differential equations and really get familiar with the differential equation solvers and the basics of using Julia for this domain, we're going to go into an example of automated model discovery with universal differential equations. So what that will look like is we'll start by doing parameter inference on differential equations. We'll do local optimization, global optimization, and Bayesian optimization, right? So to be able to get probabilistic elements. And then what we're going to do is we're going to mix diffie-q flux and data-driven diffie-q to train neural networks inside of differential equations and then turn them back into symbolic equations so that way we can understand missing elements of the models and find missing physics. So one really nice things about the neural differential equation and the universal differential equation methodologies is that they're really quick to compute, right? So these things can be optimized to be 3 seconds, which we'll be showing live in the coding. So since these things can be done live, we're going to be showing all of these results, hand, just typing it out and then training neural networks inside of these differential equations and then using them in these various contexts. The last thing that we'll get to, hopefully, is solving differential equations with neural networks and then changing your model towards data. This is one of these methodologies called a physics-informed neural network. Instead of utilizing the neural PDE framework, so we have this neural PDE.jl for training physics-informed neural networks, I thought it'd be really nice to use this workshop time to describe how can you do this from scratch. So how can you just take flux.jl, define specific neural networks with specific loss functions such that you can do the entire physics-informed neural network methodology and understand a bit about what's going on behind some of these libraries. So let's just get right into this and talk about what is scientific machine learning. So the best definition I can come up with is scientific machine learning is the mixture of scientific models, so usually things like differential equations or agent-based models or these kinds of techniques, with data-driven machine learning components, so neural networks, random forests, all these types of approximators. And the reason to do this is for data-efficient model-based decision-making, right? So the reason why people in a lot of disciplines utilize models is to be able to do decision-making, right? See what happens if you're to have a drug affect this reaction, what happens to the whole system if you're to block this, reaction of X with Y, right? So a lot of people want to do decision-making with models, but the issue with a lot of models is that a lot of them are not fully known, right? You never really know all of the chemical reactions going on in a biological organism. You never really know the true physical model because you have all of the basics of it, but you might be missing, different frictions. You might be missing different elements of, different elements of interference. And so all of these different elements can be found through these machine learning approaches and then be interpreted by bringing it back to models. So this mixture between modeling approaches and machine learning approaches is what we found to be very, very both exciting and useful. And this is what we want to share with you, just the methodology, so that way you can just type down 30 lines of code and start trying to do these yourselves. So the key idea behind what bridges machine learning into scientific machine learning is to just really understand one aspect of the neural network. Right, so we'll be using neural networks and other approximators throughout this. And one of the big questions that you might have is how do neural networks come back to being something that can be useful in a scientific model? And really the way to understand it, you just need to know this one fact, which is the universal approximation theorem. And one way to understand this is that a neural network can get epsilon close to any Rn to Rm function. So you have a function that takes in inputs and it spits out outputs, right? That's what a function is. A neural network that is sufficiently large can be approximating any of those input-output relationships over some range of values, right? So this is the training process is finding what parameters will do that. But the universal approximation theorem tells us that there is some set of parameters for the neural network that will approximate this function over this whole domain. And so neural networks, in some sense, are just function expansions. They're kind of like fancy Taylor series in some form, or fancy Fourier series, which are really good for computing, right? So all their operations are matrix multiplications, and so all these operations are very GPU parallelizable. And so it's just a way to be able to approximate functions in a way that you can quickly get back to these parameters that will be able to fit in any of these weird domains. And the reason why neural networks are really used is because they work well in very high dimensions. And so normally when we talk about a prediction problem, right, one of these regression problems or even a classification problem, what's going on in these problems is you essentially have your whole data as Rn. You know, if you have 200,000 different numbers that you're using from a picture as your input, then you have R to the 2,000 as your input to this function. And then your classification is your output. You know, it can be one value, it can be 100 values, it can be yes, no's for whether it's a dog or a cat. And so a neural network is always just something that's approximating a function. And the reason why people have started to use them is because they approximate high dimensional functions very well. And we're going to basically grab that property of neural networks, this universal approximation theorem, and then utilize this ability to approximate missing functions inside of scientific models. And that's where we start to do things like model discovery. And so the real key to understanding why we might want to do this, right? So if a neural network can approximate anything, why would we not just use a neural network on its own, right? And you might know things about, you know, big data and how machine learning is requiring all gigantic amounts of compute. And one of the reasons really then to not just use a neural network on its own is really to understand that the major advances in machine learning happened by people encoding more structure and more prior knowledge into the models that they were using. So what made machine learning take off is by adding more and more of this prior information that we have about our problem, and this allowed it to fit better with less data. What are some examples of this? Well, one of the key examples is the convolutional neural network. So the convolutional neural network, it encodes this structural assumption where you essentially assume that the pixels that are nearby in an image are more related to each other than the pixels that are very far away. And so what a convolution operation is this really just a local summation or a local averaging with respect to given pixels in a given area, right? And so it's giving you this approximation where you say, this square is all more related to each other than things over here, which for images seems to be a nice assumption. It seems to be a correct assumption. And that's why convolutional neural networks have been able to increase the amount of the predictive power that we're able to have with images while decreasing the amount of data that you need and decreasing the amount of compute. And so by utilizing structural assumptions as part of this framework for doing, you know, using these automated tools for finding missing functions, by encoding some structure to it, we can do a lot better. And so what we want to do then is we want to encode not the structure of images or not the structure of natural language processing, but we want to encode the structure of science, right? Just, you know, the big, you know, Bill Nye the Science Guy, science, right? We want to put all of that into our neural network. So how do we do that? And so what we're going to do is we're going to utilize this framework, this universal differential equation, which is a differential equation which is defined in part or in full by universal approximators. So we can say these things that can approximate missing functions can define small parts of our differential equations, and we can utilize these in many different ways. So we can use this so that way we can utilize all of our known scientific features. We can utilize all of our previous numerical methods. So if you have things like numerical PDE solvers, if you have things like models for chemical combustion, if you have models for all of these different things, you can utilize the state-of-the-art model with machine learning by putting the neural networks within those scientific models and utilizing those neural networks as components to be able to find missing parts. And so what we're really trying to do is have the neural network just cover the last mile, right? So this last mile problem is what Amazon is always trying to solve, of how do you get the package the last mile. What we're trying to do is we're just trying to find how do we get the scientific model to that last mile, right? We have measurements of all these features going on in the scientific model, but it's very common that we see something in, for example, in systems pharmacology, where we know a lot of the model, but we know that a specific part is not actually fitting to the data that we get. So what is that last change that we have to do to our model in order to correct it? This is what we're going to be learning to do with these neural network techniques. And so we're going to start with a demonstration on the toy model. I want to really get across these ideas by showcasing how we can take a toy model and utilize just very small amounts of data to be able to train a neural network within these scientifically inspired components to then be able to extrapolate well with just 21 days of data. So here what I'm going to use is a model of an epidemic. So this is a conceptual model of COVID-19 in the early COVID-19 crisis. So what this is it's a model of an SEIR. You might be familiar with this for many reasons, such as David's previous workshop on epidemic modeling. So what we have here is we have a susceptible population, we have an exposed population. So the exposed population has been exposed to the disease. The exposed population can then become infected, and then the infected over time can recover. And now we can have an integrator state tell us how many people have we had in total and how many people have been exposed in total. And we have another state in here, this D, which tells us the number of individuals who had to become hospitalized. So there's a rate at which people become infected, and then there's a rate at which people become highly infected. And now the key to this model, the key to what the researchers had to do in this International Journal of Infectious Diseases was they had to figure out, how do we make this model work out such that I can now connect with the data to be able to have this be predictive? And so they were able to utilize a lot of prior information about, we know what the rate of recovery is with COVID-19. We know it takes about 2 weeks inside of the hospital. And so a lot of these values we can just kind of put in by utilizing this information that we have from various other governmental sources. But the key that nobody knew what to do about was this this exposure value. And so what they did was they hand built this function to be able to fit the Wuhan, China measurements for what the exposure term should be in that region. What we want to do is we want to see if we can utilize the same data that they fit, their model as a form of data. And we want to see if we can find an exposure term on our own that might be more parsimonious, might be able to extrapolate well, and all these kinds of nice properties without trying to do it by hand, right? Can we automate this process of finding such a model? So the first thing that you might go to is the neural ODE, right? So the neural ODE is a very cool advance in this kind of machine learning field where you say that U prime equals a neural network, right? Why does this make sense? Well, a neural network, remember, can approximate any possible function. And so normally the way that you'd write down a differential equation is you would say U prime equals f of u, right? It's a function. But since we don't know what the function is here, or at least we're saying, let's try to recover the function directly from data. So if we don't know what the function is, we can approximately say there is a function there. We can approximate that function with a neural network under some parameters, find the parameters such that it fits the best, and that gives us the neural ODE, right? So it has some nice properties. It understands the continuous relationships that have to be true in differential equations, but it doesn't necessarily know all of the scientific information that we have, right? We know a lot more than just the things grow over time. So what all this is able to do then is if we take data from 0 to 21 days, we fit the training data in this region, and if we extrapolate out, we see that the neural ODE doesn't necessarily know how to extrapolate because the neural ODE has only been trained on this area of phase space. It doesn't really know what's going on over here, but can we give it any information so that way we can improve the way that we're doing this modeling? So this is where we can get to a universal ODE, right? So a universal ODE, once again, is a ordinary differential equation where all or part of the differential equations can be approximated by these unknown functions by universal approximators. So here, right, remember at the very beginning I said, we know a lot about the system, right? We already know, I think a lot of the audience might already know just how long do people take to recover in the hospital from this disease? Well, that's one of these rate equations. So you can specify that there must be, approximately a linear term here with this kind of rate. And you can approximate what is the percentage of people who have a severe case. You can go look up some public health statistics and approximate that, you can have the percentage go here while the other percentage goes here, right? So you can put together quite a good model, but the term that is really going to confuse you is the exposure term, right? The exposure is just unknown, right? There's so many factors that go into how people get exposed to this disease. Are they social distancing? Do they go to JuliaCon Portugal even though it's online, right? There's so many different things that can be happening that can cause exposure. And so we really don't know what this exposure function is. And it can also be determined by what country you're in, what state you're in, and how people are changing other people are changing their behavior. And so what we can do is we can say, we don't know this function, so let's place a neural network right here, right? So we have a lot of information. Let's just place a neural network in the parts of our models that we don't know. And what we can then do is we can utilize these fitting techniques that we'll be going through as part of this workshop to be able to fit this unknown exposure term. So we don't have data for the exposure, we just fit from 0 to 21. And then if we were to actually plot and see what it did, it actually learns the correct exposure terms in the background here. So it actually learns this correct missing function, at least between 0 to 21. And then we ask the question, well, what's going to happen in the future? Well, because we have a lot of the linear terms in the correct areas, they have rightly sized values, then what we can see is that it's able to extrapolate far more in the future. Right? This is not perfect. Extrapolation is a very hard problem, but from 0 to 21 days, we're able to get very good estimates of up to day 40, which is doing much better than the neural network because we've imposed so much more scientific information into the problem. Right? So this is our way to be able to use all the structure that we know. We can utilize things like known physics. We can utilize things like known chemical reactions. All of these components can be strewn together to be able to give a model that is partially there, and then try to use this neural network to complete the model. Now, can we do anything else, right? Can we extend this anymore? It turns out that we can. So one way to be able to do this is be able to take ideas from this SInDy, which is a sparse identification of dynamical systems. So in the sparse identification of dynamical systems, what you do is you evaluate all of your observables along a basis. So this basis can be a basis of functions like constant function, polynomials, sine functions, trigonometric functions. And so you build this whole matrix of your observables. And what you want to do is find out what coefficients should you multiply to your basis to be able to recover your dynamical system. Right? So if you do that in reverse, what this means is find what the coefficients would be such that when you would multiply by your observables, you would get the correct derivative values. So this gives you a way to be able to take all the data that you have and project it back down to a very small basis. Now, this methodology does require a bit of data, though. It requires good data, and it requires good derivative estimates. So in general, if we're to just take it and slap it onto something where we only have 21 days worth of data, we don't necessarily get a very sparse basis. We can then sparsify this down, and we'll show what happens when in code if we try to enforce sparsity here. Sometimes it's just not having a good time trying to find the real dynamical system if you don't have enough data, right? Because once again, this is trying to do a full recovery of the whole system. And full recoveries, they work in some sense, and in other cases, they might need some help, right? So can we mix this idea now with our idea of utilizing these universal ODEs? We can, and so what we can do is we can do sparse identification of just the missing term, right? So we have an unknown function here. We can do a lot of things, like we can build a basis of values going into this unknown function. We can evaluate what the neural network spits out, and we can do the same process, right? We can do the same process to be able to turn neural networks back into equations. And so if we do that in this case, what we find is that this neural network can be approximated by a quadratic term, right? So it gives you what the coefficients are in this basis. And so it said, no, you don't need sine terms here. You don't need cosine terms here. You don't need cubic terms. In fact, it doesn't even use this d over n term. So remember, let's use this to verify and understand what we found, right? So remember that this D term was related to the number of individuals that were highly infected as a part of this disease. And what this is saying is, in the neural network, this missing function here, this exposure term, is actually not related to D. And it turns out that was true in our generating process, and it makes sense because, if someone is highly, highly infectious, then they're instantly kind of brought to the hospital or kept away from the others in the society. And so they're not really the ones exposing others to the disease, right? It's usually people who are asymptomatic carriers that are performing a lot of the exposure. And so if you actually look at what this methodology has found, it says that this missing term inside of our differential equation is not dependent on the third term, U3, at all. And so it's able to give us this prediction, this hypothesis. We're able to verify it because we understand what the terms of our model mean, and we're only using data-driven components for small areas. And so we have all this, all this nice verifiability. And the other nice thing that comes out is that when you have sparsified models, sparsified models tend to generalize a lot better than very over-parameterized models. And so when we utilize this smaller term inside of this same method, right? So we train the universal ODE from 0 to 21 days. We sparsify the model to get the form that fits best in 0 to 21 days, and we extrapolate this out to the future. Then we're getting about at least 60 days of good predictions in the future, right? And why is this the case? Well, because now we have a model that satisfies a lot of the asymptotic properties that we'd expect to happen with epidemics, right? So we have a lot of the right properties in terms of asymptotics. We have a lot of the right properties in terms of these terms affect these ones and not having spurious relationships. And so we found a model that seems to do quite well. It's not perfect, right? Because remember that model that we started with, it had something to the 1,117th power. And so we weren't going to find the original model from the basis that we had. But we're able to find something that approximates it quite well and gives us a lot of the terms to be able to verify what was in the model. So this is the general idea behind this scientific machine learning approach, right? We're not using neural networks to predict everything, and we're not using scientific models to be able to come up with decisions on their own. We're using neural networks with scientific models to be able to recover new models and then utilize these new models to be able to understand policy decisions, understand relationships between different components, and be able to form predictions and hypotheses to guide our next data that we should collect. And so this is the general workflow of this machine learning augmented scientific modeling, right? So what you have to do, number one, is you have to identify the known parts of the model, right? So if you know anything, utilize what you know. If all you know is that the form is a differential equation, then sure, you got a neural ODE. If you know a bit more about the model, like if you know that in a systems biological model, you generally know some of the major players. You know that nanog always interacts with the SOX genes. All these different things that you can put your model together like that, and then you can say, well, I have all this data. Please tell me what I need to change about the model, right? So that's the second step. You add neural networks to capture the places where you have missing mechanisms, in places where you have uncertainty. So in a lot of cases, if you go back to the derivations of these, Navier-Stokes equations, of Bostanesky equations, if you go back to the derivations of the first order physical equations, you will see that there's terms where someone made an assumption. That assumption, normally makes sense in a given regime, but maybe that's too overreaching. Right. So what would that mean? Well, we can then say, here, I can keep this model with this assumption, but I can have a neural network capture these uncertainties related to what the assumption dropped off. And then you can train against data to be able to find what these neural networks would be to be able to fix your model to these assumptions. Next, what we can do is we can then sparse identify these missing terms to bring them back to mechanistic models. Right. We can basically go through machine learning space to go back to mechanism space by utilizing the sparse identification technique and find these missing mechanistic terms like we previously showed. And once we have a mechanistic model again, all of your tooling and all of your knowledge of mechanistic models apply. So you can verify the mechanisms by looking at what terms are related to each other, and you can extrapolate better because you have a sparsified system. You don't have one of these massively over parameterized systems. You can also use this to be able to tell you what data you might need to get to be able to further improve your model. And we'll be going into some probabilistic methods for doing these kinds of fits. And so really the idea here is to utilize all of your advanced numerical methods. So all of your partial differential equations, all of your catalytic modeling, all of these things with machine learning by utilizing this approach. So not one or the other, but utilizing it all in tandem. And we've seen a lot of cases where this has been starting to work. So one of our collaborators at CMU, they showed that if you use a universal ODE model on a battery, right? So you start from the state-of-the-art model for.
Hey, Chris, sorry to interrupt you, but I think there are a number of unanswered questions, mostly with regard to where your slides are and the Git repo for this workshop. Sorry, it's just getting a lot of traction in the Q&A, so I just thought I'd remind you.
Yep, the slides will go on afterwards, and the Git repos that we'll be using for this workshop are just the public Git repository. So the differential equations documentation, the diffie flux documentation. I'll be walking you through all this documentation.
Oh, okay, right.
Yeah. What I really want to do with this workshop is I really wanted to show everyone how do you do scientific machine learning, and giving you a small tutorial isn't going to help in the long run, right? In the long run, the right thing to do is to understand our documentation to be able to know how to get more help in the future. So what I'm going to be doing is I'm going to be going through that documentation and using that as my resource. Yeah.
All right. Thanks, Chris. You can continue. Thank you.
Yeah, so our collaborators at CMU had showed that you can take a state-of-the-art battery model for how it degrades over time and be able to use this to be able to use a neural network within this differential equation model to be able to improve the model by 19%. So this is, not a small change to what is already a state-of-the-art model, and be able to get predictions that are much better. So this new self-fit mechanism, it was looking at being able to do, battery-powered aircraft by finding out exactly how this degradation occurs, and utilizing these universal differential equation techniques are getting them over that last model and getting them, from what the state-of-the-art first-order physics is to cover that last area by integrating the data that they have. We're utilizing this in other scenarios. So, for example, what we're doing is we're taking this approach, be able to quantify what the quarantine strength is within COVID-19 to be able to generate, this worldwide data set by state and by country to be able that has a quarantine strength, and then we verified this methodology against a lot of different case studies. And so now what we have is we don't just have time series for how the disease has progressed, but we also have the time series for how the quarantine strength has occurred in many different countries. And hopefully this becomes useful for different researchers to be able to understand how different areas have been affected by the disease better or worse. So all of these have been showing ODE examples, right? So just ordinary differential equation examples. We can move to something that's a lot more difficult. Now, I'm going to say as a warning here that these next few slides, they're meant to be for people who are very familiar with scientific computing. Right? So we're going to be mentioning things like partial differential equations, neural stochastic differential equations. If some of these next few slides are over your head, that's okay. Take in what you can. What we really want to do right now is I just want to demonstrate what are some of the more difficult non-toy problems that these methodologies have really been looking at that are beyond ODE models. So one way to be able to make use of these is universal differential algebraic equations. So in some cases, you do not know the whole system, or you do not know how all chemicals interact, but you might know some conservation laws. So for example, this example comes from a chemical kinetic system where we know, for example, we know a first order interaction causes the chemical Y2 to go back to Y1, but Y1, Y2, and Y3 are all the same chemical. And so we're just trying to model what is the percentage of them in each of these three states. So since we know that it's a percentage, right, we can then say, well, there's a conservation law that the percentages always have to add up to 1. So this is the model that we have. We have a differential equation where we know components of it. We have neural networks covering the unknown components. And then we have these conservation laws that are saying, here are the things that we don't know about. And we can write down this mass matrix DAE, right? So I'll showcase how to write down DAEs such that we now have a neural network that covers what's unknown, and we have the conservation law encoded in the way that we do this singular mass matrix. And then all we have to do is we have to have a differential equation solver that is able to handle singular mass matrices to be able to then recover what this missing equation is. And so we can learn highly stiff equations by utilizing this kind of methodology by integrating these all this kinds of knowledge of conservation laws into our system. So if you have conservation of energy, if you have conservation of mass, all these ideas can be encoded into our machine learning framework by utilizing this general technique. Another way that this can be used is to be able to discover partial differential equations. So partial differential equation discretizations are simply a form of a convolution, right? So if you look at this discretization of the Laplace equation, so it's a discretization of the second derivative in two variables or in two dimensions. If you look at what this is, it's the same thing as a stencil where you say, at this point, take the value above, the value to the left, the value to the bottom, the value to the side, and -4 from the middle, right? That's what this stencil is saying you should do in constant or in dx equals dy. So now what you can do is you can say, well, this is a stencil, and so these are the coefficients of a convolutional layer that would give us something that's equivalent to this partial differential equation. We can then use this in reverse and say, if I had a partial differential equation, I can represent the universal partial differential equation by a neural network and a convolutional neural network, and I can train the convolutional neural network and neural network in tandem within spatiotemporal data. And then what comes out is it tells you what the convolutional neural network's weights tell you what derivative operator should have been. So you can use this to recover that you had a diffusion operator. And then the other term gives you what your nonlinearity was. So this can tell you, hey, you were missing, one of the terms in your differential equation was a quadratic term. And you can utilize these same approaches, the SInDy sparse identification on just this neural network to recover the actual equations that were missing from this differential equation. So you can utilize these same techniques on partial differential equations. So it's able to be applicable on these temporal models, spatiotemporal models, and beyond. Other things that you can do with this methodology is that you can embed neural networks into scientific simulation in order to accelerate the scientific simulators. So for example, in non-Newtonian fluid simulations, you have these systems of differential algebraic equations. Well, what we can do is we can find a system of ordinary differential equations that is parameterized on the physical components, and then we can figure out what are the ODEs we should be writing down that would approximately be these differential algebraic equations. And we're able to get a 2x acceleration by training this neural network and then by utilizing these ODEs instead of the original DAEs. So you can utilize these neural networks to convert between these scientific forms and gather different information or accelerate your simulations. We're able to show this inside of accelerated climate parameterizations so if we're working with the people for the climate model, and what's generally done there is you take these Bostanesque equations as your kind of truth, right? This is how in some sense, it's a nice approximation for how fluid flows occur within this global climate model. But if you're to try to apply these Bostanesque equations throughout the entire Earth, then you would never be able to simulate anything. So what you can do is you can take an integral along the xy plane, and then if you do this averaging approximation, you can get a one-dimensional partial differential equation where you have a missing function in there. And what we can do is we can then fit the missing function, and suddenly we have a nice way to be able to, this is called parameterizing the climate model. We have a nice way to be able to get a much faster form that has a lot of the same physical properties, but as the original equation, but means that we can now solve one-dimensional PDEs instead of three-dimensional PDEs in a way that's automated, in a way that we can just take data and be able to find what this approximation should be doing. So universal differential equations as a methodology, the reason why we've been really focused on them is because they extend a lot of previous other methods, right? So there's been a lot of other methods coming up in the scientific machine learning space, and we can showcase that a lot of them actually fall into just specific choices of universal differential equations. So which really gives us a way to start to approach this problem, right? Because then we can build a software that handles universal differential equations well, which then will mean that it will cover these other algorithms as special cases of that same methodology. So for example, there have been 2 studies about these learning physics-informed neural networks with discrete forms. So if you discretize your physics-informed neural network or utilize a multi-step neural network, these kinds of methodologies are essentially a universal differential equation with the multi-step integrator where you set adaptive equals to false. And so, if we look at these techniques, we can say, well, here we can write down the universal differential equation such that when we call this ODE solver on this UDE, we recover these previous methods, which authors have been able to show give you high accuracy on. It gives you high accuracy with just small amounts of data. Right, so we're able to recover a lot of these other types of methodologies by utilizing these techniques, and then we extend them as well, right? So if you wanted to extend these previous papers to utilize, implicit methods, strong stability preserving methods, Runge-Kutta-Chebyshev methods, if you wanted to embed them in stochastic differential equations, differential algebraic equations, delay differential equations, all of these things can be done just by choosing a SDE problem inside of differential equations.jl, sticking a neural network in there, and then telling it to discretize it. So basically, this methodology gives us a very powerful way to be able to build one software that can cover a lot of different cases. We can even see this this is probably the most extreme example of where if we want to solve these semi-linear parabolic equations, what you can do is you can demonstrate that there's this forward-backwards stochastic differential equation, which under a certain loss function, if you fit that, then you'll recover the solution to this partial differential equation. Now, the way to be able to extend the previous work is to understand all you have to do is you have to define this SDE where you have the same neural network showing up in these 2 spots, and there you go. This is a universal stochastic differential equation. If you're to do a Euler-Maruyama discretization of this stochastic differential equation, then you recover these methods that people have been able to show can solve 100-dimensional Hamilton-Jacobi-Bellman equations. But then you can extend it, right? You can utilize high-order methods. You can use implicit methods. You can utilize adaptive SDE solvers, and now you have new variants of these pretty state-of-the-art methods just by applying, this universal SDE solver or universal SDE training mechanism to this definition of an SDE. So there's a lot of new ways that people are showing that you can solve partial differential equations fast with neural networks, and these all fall under this universal differential equation formalization. And so in some sense, UDEs are the BLOS or LawPack of SciML, right? They're the way that people really started to do scientific computing fast was to realize that if you get matrix multiplication fast, then everything else seems to follow, right? And what we're doing is we've noticed that this universal differential equation is kind of a general form which we can fit a lot of these other methodologies into. And so if we can specialize a software to be able to do training of universal differential equations in their fastest form on CPUs and GPUs and with MPI and all these other things that are in there, then we can cover a lot of different cases and be able to handle a lot of different methodologies. So what we noticed then is that scientific machine learning requires the efficient and accurate training of UDEs, and that's what a lot of the scientific machine learning or this Julia SciML ecosystem is built around. How can we do all of these different techniques with universal differential equations to be able to recover all these different scientific machine learning techniques and be able to get a very optimized solver that is able to handle, that is able to be fast, is able to be accurate, is able to be that you're able to introspect and be able to understand all the pieces of all these different properties all in one ecosystem. And so this is the Julia scientific machine learning ecosystem. I'm just going to be describing a few of the packages here, and then I want to go through some of our web components and be able to describe what our offering is and be able to how to find the components. So one of the core centerpieces that people have been using for years now is the Julia differential equations.jl package, which is high performance differential equation solvers. Right? Differential equations are at the center of all of these different problems, and so it's no question that differential equations comes highly into play into all of this. The next piece is diffqflux.jl, which is universal differential equation training. It also has some optimizers. It has a lot of choices and documentation of sensitivity analysis. So you can do all these different techniques like discretize and optimize and discretize, differentiate through ODEs, SDEs, DDEs, DAEs, all these kinds of things with specialized layer functions inside diffeqflux.jl. Modeling Toolkit adds a symbolic component to the ecosystem to be able to do automated optimization and parallelism. There's a whole JuliaCon talk that will be about that. There is a neural PDE component, which is building out these, these high-performance, high-dimensional PDE solvers, like physics-informed neural networks and DPSD methods. So that way, if you have, for example, a financial problem where you want to just solve a, 1,000-dimensional nonlinear black Scholes, then these methods are already ready for you to just write down the equation and have it automatically solved using these techniques. Other components are things like catalyst.jl for chemical reaction networks and differentiable molecular dynamics components, and also data-driven diffeq for these Koopman methods and also these sparse identification methods. These are just 50 of the libraries out of, these are just a few of the 50+ libraries in the Julia ecosystem, and so I'd highly recommend that you check out all of our other resources. And let me demonstrate this here.
Chris,
So,
again, sorry to interrupt, but
yeah, this is a good
I
time.
was just going through, I was just answering some of the questions, and I saw quite interesting one that you might want to go into a bit more. Somebody asked how all these techniques that you're talking about are different from the classical systems identification methods.
So a lot of them are related highly to these classical systems identification methods. In fact, some of these packages do a lot of the classical systems identification methods as well. So you can, in diffeqflux.jl, you can utilize layers that are spline layers, and you can utilize things like classical collocation methods, and you can utilize things like, what's the word for it? Multiple shooting techniques, right? So you can incorporate all these ideas because what scientific machine learning is doing is it's really just bringing the neural network components in. Now, where this is improving upon what was before is that this is making it so that way when you put neural networks into these differential equations, it will automatically make use of this reverse mode AD, and it will perform backpropagation for doing the adjoint calculations. So this is more of it's more of a technical detail that whenever you have a vector Jacobian product, you can always utilize a vector transpose times Jacobian. You can utilize reverse mode automatic differentiation. And so instead of using numerical techniques like in previous packages like sundials to be able to write down these adjoint equations, we make pervasive use of automatic differentiation for all these calculations to be able to reduce the computational complexity.
Yeah, I just to add to that, I also think that these new techniques do better than the classical systems identification techniques because those techniques try to find try to learn an approximate model, which is often linear or something like that with some nonlinear terms. They aren't actually representative of the actual dynamics. Whereas with techniques like SInDy, we try to do better by trying to actually learn the underlying dynamics in a more concrete.
There are some classical techniques that were nonlinear as well.
Sure.
Though a lot of what we've been doing here is we've been making it so that way they can scale to very large cases and be able to do the GPUification. And there's been a lot of focus on different ways to be able to use these nonlinearities. So a lot of the classical systems identification techniques and ideas, they shouldn't be forgotten about. In fact, a lot of them are utilized in these libraries, and you can find documentation pages doing exactly a lot of what you might find in MIT system identification class. So yeah, there's a big relation between scientific machine learning and systems identification or control theory as well that you would find in previous engineering software and things like that.
Okay. Thanks, Chris. Please continue. Yeah.
So yeah, so what I want to do is I want to show where you can find all of our tools for scientific machine learning. So we have a brand new website up, which is at SciML.ai. And at SciML.ai, we give a quick introduction to what a lot of these different packages are. So these same ideas are showcased here. For example, differential equation solving, physics-informed model discovery and learning, compiler-assisted model analysis. We won't necessarily be going into this set of tools because that'll be a different JuliaCon talk. But please go see the talk on automated parallelization and automated optimization. We have differentiable scientific data structures and simulators. So all these different things are mentioned here. If you want to find the documentation for a lot of our different packages, you go to our documentation page where you can find, for example, the documentation for differential equations.jl, which is an extensive documentation of how to use the differential equation solvers, both in the scientific machine learning ecosystem and beyond the scientific machine learning ecosystem. We have our SciML tutorials page, which is also found at scimltutorials.jl, which describes how do you do a bunch of things like differential equation modeling, how do you do conditional dosing of these pharmacometric models, how can you utilize numbers with uncertainties. A lot of these different odd tutorials are found here. You can find all of our benchmarks. And then we can also find how to utilize our differential equation solvers from Python and R. Right, so these are fully described and documented, and there's a lot of automation going on for the installation process for those. Now, beyond that, we also have a lot of tools. For example, neuralpde.jl is one of these newer libraries for these automated PDE tools, where you can find out how to do things like solve the two-dimensional Poisson equation from a purely symbolic description. So here we have a mathematical description of the Poisson's equation. Here we give it a symbolic form where you say, the second derivative in x plus the second derivative in y is equal to minus the sign, signs multiplied together. You say what your domain is, then you define your neural network, and then it will just solve the equation and be able to use that to be able to give you the solution to the Poisson equation. Right, so that's a neuralpde.jl, which falls into this whole class of diffq operators and phoenix.jl of different tools for partial differential equations. We have tools for scientific machine learning model discovery. So then the core here is going to be diffq flux, which has extensive tutorials in doing things from fitting neural stochastic differential equations to utilizing Hamiltonian neural networks and graph differential equations. So, if you know that your system is a Hamiltonian system, you can specialize on all these different ideas. We also have a lot of modeling languages and domain-specific tools. So, for example, modeling toolkit.jl is a full modeling language that allows you to take existing codes and automatically parallelize them in specific ways and automatically do, generate codes for the Jacobians. We have other tools like N-body simulator, which is a differentiable system molecular dynamics kind of simulation library, where you can be able to utilize, electrostatic potentials, or utilize other things like different thermostats to be able to describe these large molecular dynamic simulations. And so, you can get started in scientific machine learning not just from scratch, but by utilizing these tools to get you 90% of the way to your problem. And then what a lot of people make use of as well are some of our numerical tools and primitives. So for example, exponentialutilities.jl is all about how you calculate, exponential exponentials of matrices times vectors really fast. So exponential of t times a, 2 times a vector. How do you do this calculation fast is what this entire library is about, and we're adding differentiability to it as well. So, quadratures, how do you do high-dimensional integration? How do you automatically detect the sparsity patterns of codes? All these different things can be found from this page, which leads you to the documentation throughout the SciML ecosystem. If you're curious about all the different things that we're working on right now, you can check out our roadmap, which describes the full study of what we're doing with the SciML ecosystem and a lot of the different directions that we're going. If you want to, if you utilize our work, you should check out our citing page, which describes what you should be citing as you utilize these different components. If you want some data to get started with, right? So if you say, I want to do scientific machine learning, but I don't know what data I should use, well, then you can check out our challenge problems page, which we'll be getting into later in this. If you want to know where to get help, you can check out our community page, which has all of our community resources like our GitHub organization, how to find us on Discourse, and how to find us in the Gitter lobby or in the Julia Slack. This is linked to our Julia Slack channel, and so there's always an ongoing discussion of how to utilize these techniques inside of here. If you utilize our techniques, or if you're in the general community of scientific machine learning and just want to chat, these are great places to be. If you want to know about all of our newest developments as they come out, you can see our news section. So for example, as things come out, we put out these blog posts that are describing our new libraries and how we can do things like automatically generate code for C, MATLAB, and Stan from these Julia ecosystem tools. And last but not least, we have our SciML showcase, which describes what are different libraries that are utilizing SciML for quantum optics, for climate modeling? What are different libraries for that using? What are different press releases that have been focused on scientific machine learning with our tools? What are given books that have utilized our tools? What is it? Here we have a whole playlist of 44 different videos that have utilized these tools from different JuliaCons. And then we have a lot of different blog posts that have come from beyond the general community. So if we're missing any of your resources and if you put something up and you want us to add it, please open a pull request because we'd love to share these with you. And all of our source code is then online inside of our GitHub repository. So these are the general tools that we have, or these are the general ways to find the right documentation and find out what you're doing. What I want to do now is I want to get into why is this scientific machine learning ecosystem one that you might want to take note of? So actually, this is a good time now to take questions. Are there any questions I should know about?
Not that many. I think you can. Actually, could you open the Q&A tab? Maybe you can just go through the top 3 or 4. They've all been upvoted.
All right, let's see.
You could dismiss them if you already answered them.
So can we run SciML online? If you mean using cloud resources, yes, there's a lot of different ways to make use of cloud resources, like AWS, for being able to utilize these. A lot of our collaborators are utilizing clusters and cloud systems with their GPUs to be able to run high performance simulations. So you can utilize these tools online. Let's see.
Somebody's asking whether you could use other universal function approximators.
Yes, you can utilize a lot of other universal function approximators. So I'm going to demonstrate just a small part of the diffie-q-flux library. But if you go to the diffie-q-flux library, you can find that there are these tools like classical basis layers. So you can utilize function approximators like Chebyshev basis, sine basis, Fourier basis, Legendre basis. You can tensor product them together. And you can also utilize cubic splines or any spline actually from the data interpolations.jl. And you can also utilize things like collocation methods. So this example showcases how you can do a smoothing collocation, use this to generate derivative data and directly fit the derivative data. So yeah, you can utilize all these other universal function approximators. The classical ones, because they have to be built up to high dimensions by utilizing a tensor product, they don't scale as well to very high dimensions. But if you have a 2-dimensional function, it's probably even better to utilize just a Fourier series. Now, since this is mostly a tutorial to be able to show people how to utilize the tools beyond what they learn here, we'll be using neural networks everywhere just because that's a nice tool to be able to then, you change a number from 2 to 100 and the same technique works. And so, but if your problem is more constrained to these smaller spaces, please feel free to utilize these other aspects of the libraries. Let's see. Yeah, so so I think that's most of them. I'll get back to that when we're doing the coding section, but I think that covers the general idea of that. So let me get back to the slideshow. So we'll get to the live coding section after this part. So why do people utilize the SciML ecosystem? Well, it tends to outperform a lot of the different tools in other ecosystems, in both high level and low level languages. So here, for example, are 2 different benchmarks on stiff equations. And so here we show that on the high res equation, we have that the differential equation methods are more aligned with something like sundials, directly using these sundials as C++ methods or directly using some of these Fortran methods. We can call out to things like RSD solve, like SciPy. We can call out to MATLAB, and we see that there's about a gap of 50x to 100x between these high-level language and low-level language tools. We then start to do a lot of benchmarking on the low-level language tools, right? For example, over here, then what we can see is that we don't win in every case, but in a lot of cases, the pure Julia differential equation methods do outperform things like for the Fortran-Radow methods and the C++ methods like CVOD, BDF, right? There are regimes where, for example, the Fortran-Radow method does very well for very low tolerance equations, but changing between the pure Julia methods and the non-pure Julia methods is just one line of code change. And actually, you can utilize all of these techniques for universal differential equations with our wrappers to sundials and the Fortran methods and all of them as well. So speed really drives a lot of researchers to the Julia SciML ecosystem. So for example, what we did, what we showed before was that if you take the Lorentz equation and you just try it in a few different neural network combined, differential equations ecosystems, then we saw that, differential equations.jl for forward pass will be able to solve it in, 1.67 milliseconds. From the authors of JAX, we found out that it's able to do it in 3.6 milliseconds. And if you tried this in TorchStiffyQ, you get 48 seconds, right? So for very small equations, we have differential equations.jl optimized. For very large equations, we then have things that will utilize MPI, and are working in climate model scale. For example, what's going on with simple neural ODE training, we'll show live how you can train the neural ODE from the original neural ODE paper in about 3 seconds. Whereas for the original tools, this was about 300 seconds. So we find that a lot of researchers are being drawn to the Julia SciML ecosystem because of the speed that you can have in these different scenarios and a lot of the flexibility. Here is a huge list that kind of describes a lot of the tools that are available out there. So some of the best tools for this before are always these tools in C++. So Patsies TS has a very good adjoint system. Sundials also has a very good system for getting for solving differential equations and doing sensitivity analysis. But what you find with this Julia scientific machine learning ecosystem is, for example, it's really not just one package or not just 1 or 2 developers. It's kind of an ecosystem of 30, 40, 50 people at this point. And so there's hundreds of methods tuned to different problems, right? You can go through our benchmarks and see, I think that at this point, there's about 30 to 40 different problems where there's different methods performing well or worse in different areas. And so by having all these different choices, you can get really well tuned to these different scenarios. One of the key things that really sets apart the Julia scientific machine learning ecosystem from some of these other tools like TorchStiffyQ or JAX is really the tools that we have for stiff ODEs and DAEs. So people who do scientific modeling, that almost every equation tends to be stiff, right? All of your chemical reaction networks, any discretization of partial differential equations. And this is really where the classical C++ tools and scientific machine learning ecosystems have really been focusing over years to be able to develop really highly tuned, highly efficient methods. Now, one of the key advances of the Julia scientific machine learning ecosystem is the fact that we have all these different sensitivity analysis methods. I'll go into a second why this is important, but there are different methods for computing these gradients with respect to differential equations. So you can reverse an ODE, which is going to be the fastest method, but it's also it can also go wrong on very stiff equations. So you want to have that method available, but you don't want it to be your only method. You can have stabilized checkpointing, which can utilize some aspects of which basically can utilize some aspects of the adjoints to be able to, in a memory efficient way. But other research has shown that it's not the most accurate method for sensitivity analysis. The most accurate method tends to be this discretize and optimize approach, which is equivalent to differentiating the solver. Now, if you look at these other ecosystems, you have things like Sundials, which has a stabilized checkpointing method. You have Patsies TS, which has recently come out with a discrete sensitivity analysis. But you don't really have tools that are combining all of these techniques together to allow you to just do a one line flip between them, and in a way that is also integrated directly with neural network libraries. Now, just like these classical libraries, we have C++. Just like these classical libraries, we have tutorials showing how to utilize this with MPI, with multi-threading in GPUs. We have event handling, right? So we'll demonstrate an example of that, where you can say whenever a value hits 5, do a certain event. We have a lot of techniques for stochastic differential equations, which includes methods that are stabilized, like SROC methods. We have high order strong methods, high weak order methods. For non-diagonal equations, commutative equations, all these different equations we have specialized on different techniques, and they all have adaptive versions. And then we also have a lot of techniques for delay differential equations, and I'm just I'm not even going to go into a lot of the things like stochastic delay differential equations, differential algebraic equations. What are some others? PDMPs, so when you mix together, when you mix jumps with these equations, there's a whole bunch of these other types of equations, which we won't even mention here, but so the Julia SciML ecosystem is really pulling together a large set of methods that are all differentiable under one hood. So I want to go into a second, what do these features mean, right? Why should you care about having all these different techniques for computing adjoints? And why do you need techniques that are stiffness aware? Right, so one of the keys is that this Julia SciML ecosystem is not just for speed, it's really about its flexibility, its accuracy, and correctness. There's going to be some expert talk here, but I really want to showcase a few of these examples of how some methods can go wrong and how utilizing this ecosystem can make sure that you can be robust to these different scenarios. So I want to start by saying that this Julia SciML ecosystem is very meticulously tested. So for example, our ordinary differential equation solvers go through 6.5 hours of test for every single change, and it checks things like how events, gradients, GPUs, convergence tests on a bunch of different problems. The SDE solvers check their distributions on analytical solutions and against each other. All these different techniques, all these different problems are checked whenever we do any code updates. And also when we have a version that is related to a Fortran code, for example, like DP5 is supposed to be our version of Dupree 5, we have tests to be able to make sure that it's actually exactly getting you the same values. This actually has a funny story here that is related to our testing, in that in order to get the same value as the original Fortran Dupree 5, you do have to specify an initial DT, because the original Fortran method actually has a bug in the way that it does its initial DT calculation. So these, the SciML techniques have been utilized to be able to not only, be a form of check for correctness, but also a way to be able to check for correctness of even traditional methods and find bugs there. So one of the things that can be happening when you do scientific machine learning is you can have properties like stiffness, high Lyapunov coefficients, and these kinds of techniques that can make very simple assumptions on the numerical forms fail. So for example, a lot of these other techniques that I mentioned require reversing the ODE. And they might require that you use a non-stiff ODE solver, right? Well, there's a lot of cases where those will either fail or give incorrect results. So here, for example, is the Rober differential equation. This is one of those classic equations that was used since the 1960s for chemical combustion. And if you try something like the Dupree method, so either the ones from pure Julia or the one from ODE interface, so the Fortran method, you'll see that the Dupree methods just fail, right? You do the same thing for the SciPy one. They're all calling the same method. And so this method doesn't work because this equation is too stiff. Right, so you need to have stiff tools if you're going to do some things like chemical combustion equations. Now, the other thing that can go wrong is if some methodologies require reversing the ODE. And the reason why we don't require that for all of our adjoints and why we have these different choices is because you can, for example, solve this equation forward, you can solve it in reverse, and see that numerically you end up at two different steady states. You don't end up in the same place as you go backwards, right? So there are ways such that if you have equations that go to steady states, they might get stuck at the steady states. If you have highly stiff equations, then you might not necessarily take the same inverse. All these kinds of problems can go wrong when you're working on highly stiff problems. And the Julia SciML ecosystem has really been built around making sure that we can correct for these issues and be able to handle these difficult scientific models. So a lot of researchers have been demonstrating that ill-conditioned gradients can cause a lot of difficulties in scientific machine learning, specifically if you have stiff equations, the gradients that you have or the Hessians of the optimization system can have very high condition numbers. And so you can demonstrate that these condition numbers scale with the stiffness of your equation. And so standard off-the-shelf machine learning tools like stochastic gradient descent they're really related to the Euler method in optimization space, and they don't work well on these stiff problems. So we've been building out a lot of our own, gradient tools, a lot of our own optimization tools, a lot of our own approximation tools, specifically to get around these problems that happen with off-the-shelf machine learning tools if they're to be applied to this domain. And so we have a lot of features to be able to handle stiff ill-conditioned systems. One of the systems I actually mentioned earlier was a system that had a Hessian condition number of 10 to the 13th. So you have to be able to make use of things like fast methods for float 64s. You have to make use of things like discretize and optimize approaches to be able to handle those problems effectively. You have to utilize adaptivity in the right way. You have to utilize high order. All these things have to come together. And so what we're seeing with this JuliaCon ecosystem is that a lot of other researchers are using it as a tool to be able to even understand how these different techniques for gradients work. Right? So there's a whole really nice paper on discretize and optimize versus optimized and discretized methods for training things like neural differential equations. And this was all conducted using the scientific machine learning ecosystem. Now, this is the most extreme of the examples, but for the expert in there that wants to know, what features do you have that are related to these very large climate models? Well, we have all these things for batching on GPUs, high-order adaptive implicit ODE solvers, matrix-free Newton-Krylov with preconditioned GMRes and checkpointed adjoints, right? All these things that are required when you get to very large, very stiff partial differential equations. You can utilize these with neural networks in there, and you can train them in this context. So that is why you might want to use the JuliaCon ecosystem. And so the next thing I want to get into then is, well, let's just start to do some modeling. So let's start doing some live coding. And live coding to this many people online is definitely very scary, but hopefully it should all work out. So the way that you get started with the Julia differential equation ecosystem is you define a differential equation. You can utilize this differential equations.jl, which is pulled in by using differential equations. And Ranjan, at any time, please stop me and just ask me the questions. I find it a little bit difficult to read the Q&A at the same time.
Yeah, for sure. Yeah, I will let you know.
Let me know. Yep. So the way that you get started is you do add differential equations, and this would add the library. I'm not going to do that right now because it's already added. And so if I want to know what my current state of my packages is, you can do st, and then you can see what packages you currently have. Let me actually zoom in a little bit to make my screen a little bit nicer for the presentation. So here I can see that I have developer versions of the differential equation library, some of the differential equation libraries. I have differential equations.jl at version 6.15. And so using this st is stands for status. It's a very good way to be able to know what packages you have installed, what versions you have. And you can use this to be able to compare against the websites. We will know whether you have the latest versions. So how you would do that is you would, for example, go to differentialequations.jl. Let me get to that. So I can go to differentialequations.jl and see here you can see that the latest release was 23 days ago and it's version 6.15. And so I'm using the latest version and should have a lot of these latest features. You can, it shows up in the same place on the diffkey flux repository, on neural PDE. And so for all these, this is a good diagnostic to know where you are and what packages you have. Now, a lot of these latest techniques in scientific machine learning will require that you're using the latest Julia version. And so we recommend that you use Julia 1.4 or higher, which is what I'm demonstrating here. So let me throw this REPL down over here again, and let's get started on some coding. Right. So what I want to do first is I want to look at this Lotka-Volterra equation. So yes, I know that some people had a bet going on of what slide I will first show the Lotka-Volterra equation. It is slide 43. So with the Lotka-Volterra equation is a quick and simple model for a small ecological system between rabbits and wolves. So here we have the rabbit dt. So the amount of rabbits over time changes by rabbits undergo exponential growth, and then they get eaten off by wolves. And then we have the number of wolves changes by, well, the number of wolves grows if there's more rabbits because there's more food, and then it decreases if there's too many wolves because of competition. So let's write down this model, right? So we can say my function that I want to approximate is the Volterra equation, and I want to describe this in terms of my state, my parameters, and time. And so what I want to do here is I want to say, well, let's use the way the equations are written down, right? So you always want to match the way that you're doing your scientific model because that makes it easier to read. And so here, since our original source was showing D rabbit, let's use D rabbit and let's use D wolf. Right, and now we have these parameters alpha, beta, gamma, and delta equal to P. And now what we want to do is we want to say the first the first variable the first ordinary differential equation is equal to D rabbit, which is the same as alpha times rabbit minus beta times rabbit times wolf, right? And then our second equation was the wolf equals gamma times rabbit minus gamma times rabbit times wolf it's plus gamma minus delta times wolf, right? And we can look at this and see, hey, if you have more rabbits, you're going to get more rabbits. And oh no, when you have a wolf next to a rabbit, you're going to get less rabbits, right? And we can also look at the pictures here and see that, oh, this wolf was hungry, eats this rabbit, and you get more wolves. And if there's too many wolves around, you're going to get less wolves. So this is the Volterra equation. The way that we define a ordinary differential equation is u prime equals f of u. And so, u prime equals f of u, if we're going to write this. So what we need to do is we need to say that this is our f. The other thing that we need to have is u prime equal, or u of 0 equals u sub 0, right? So we need to define our initial condition, and we need to define the time span that we're going to be solving on. So here what I want to say is that u sub 0 equals 1.0, 1.0. So I want to say that I'm starting with the same number of rabbits and wolves in non-dimensional numbers. So non-rabbit wolf dimensional numbers. Now for my time span, I want to simulate from 0 to 10. And from here, I can make this a problem, which is an ODE problem, which is defined by this Volterra equation, my initial condition, my time span. I also want to give it parameters, right? I need to tell it what I want alpha, beta, gamma, and delta to be. So here I want to say P equals 1.5, 1.0, 3.0, 1.0 is a very nice model for this. This defines my ODE problem. And how do you solve this with differential equations in .jl? You just do sol equals solve this problem, right? And it'll pick a method to solve this. So here you can see that it picked the sit5 method with Rosenbrock 2.3. So it's able to automatically detect stiffness and switch between a non-stiff method and a method for stiff equations, and it solves this in 25 steps. And then what we can do is we can plot this equation. So you can say plot the solution, and we see that this is our Volterra equation. So we can also look at things like the what's the word again? The phase diagram by saying let's plot variable 1 against variable 2, and here we can see that we have our rabbits and wolves creating this cyclic dynamics like we'd expect. Now, the way the solution object works is sol.t is our time steps, and sol of t, or sol of I, like for example, sol of 5, gives us the value that occurred at the 5th time step. So sol.t of 5 was 0.561, and sol of 5 is the value of the time series at that time. So here it would be probably around here. And we would see that, yeah, it corresponds to about 3 and 0.8. Right. We can also get the value at arbitrary times, for example, by doing sol of 0.75. So it doesn't matter that whether we step there or not, we can get the values at these specific points. We can say, we can use this to hone in on what the maximum value is here. And yeah, so you can use this as a function itself within optimization libraries to be able to optimize the t and find where the peaks of these equations are and all sorts of other problems. So are there any questions then related to ODEs? Well, I forgot to mention that the way that you then control the solver, so differential equations.jl, if you're first getting started with differential equations.jl, I would highly recommend you use this ordinary differential equation tutorial. Most of the tutorials and most of the documentation mentions at the top that we assume you have read this tutorial. So this is the basics for how do you do things, like choose what tolerances you want to use and choose what differential equation solvers. How you do that, for example, is if you don't want to use the automated approach, you can say, I want to just use sit5, and this will then compile a version which solves a sit5 and solves the equation with this other differential equation solver. We can then change.
Just a suggestion.
Yep.
So as you go through the programming, could you also, if this is in the documentation, maybe go through the documentation and copy and paste, and then, just so people know where they can build these scripts from.
Yep.
Right? If they haven't seen something like this before, then yeah, exactly.
Yeah,
right.
So this documentation actually has a full work-through example on a different set of equations, the Lorentz equations. So if you're new to the ordinary differential equation modeling with parameters and all that, please check out this exact portion of the documentation. It is the first tutorial that shows up when you go to differential equations.jl. And this is at diffeq.sciml.ai. So yeah, so one of the key things to be able to optimize the differential equation choice in many different scenarios is this choice of ODE solver. If you don't know what you're doing, that is completely okay. Just leave it blank, and it will give you an efficient method for any of these different equations. Now, if you do know what you're doing and you want to look at the documentation and choose things, well, the tutorial describes what some of the top methods would be for different scenarios. And then if you dig into the ODE solver choices, you can see, for example, here are some translations from R. So ODE 2.3 is like BS3. ODE 4.5 is like SIT5 that we would recommend SIT5. So there's all these different translations. There's a whole discussion of which methods you might want to use in different tolerances. And then there's the whole description of these other differential equation solvers you can choose. I will not have time to go through all of this. This could be a multi-hour talk in itself about how all of them are optimizing for different scenarios. But we can, for example, pull in something like sundials, which someone asked a question about. We can pull in sundials and we can say CVODE BDF. And now we are using sundials instead of the pure Julia methods, right? It's that simple to be able to switch between them. And so we highly recommend that you utilize all these different methods, right? And the adjoints will apply to these different methods as well. So that's ordinary differential equations. One last thing that I really want to make note of is the saveat command. So one of the key points, one of the key pieces of our tutorial is of our documentation is this common solver options page. So there are many different packages that feed algorithms into the common solver interface, but they all rely and act on these same keyword arguments in the same way. So if you utilize these keyword arguments, you'll be able to parse the solution and be able to play with it in the same form as you switch between packages. So as you go from Sundial C++ to Fortran, they will all act uniformly. And the way that so this describes how you do things like set different tolerances, how you set the initial DT size, how you set DT max and DT min, but also how you do things like control the amount that's saved. So by default, the differential equation solver saves enough to be able to build this continuous solution, which has a lot of these extra details and components in here. So if we throw this into the REPL, we'll see that we have not just a solution to fifth order, but we also have an interpolation giving us a continuous fourth order solution. And it tells us what time points and what values were computed. But we can say instead that we only want you to save that every 0.1 time points. And so if we look at what's computed when we do this, then we see that we save at 0.1, 0.2, 0.3, etc., getting 101 points, right? When we do save at, the interpolation no longer saves all this extra data, and it tells you that it's only saving the values at these specific points and giving you a linear interpolation. We can also change how much we're saving by doing something like save every step equals false. And what this will do is that this will only save at the start and the beginning. So that way we can, for example, if we do a partial differential equation solve, we can save a lot of memory. We can also do something like save start equals false. And you can probably guess what that's going to do. And now we only have the solution at the end. We could even do something ridiculous and say save n equals false. And we can come up with a solution that is completely empty. And I'll describe reasons why you might want to make use of that. If we want to do the adaptive time stepping, but we just don't want to have an interpolation, then we could do dense equals false. And this will give you the adaptive time stepping without any of the extra features that are required for the interpolation, because the interpolation is the most memory intensive component. So for example, these are all contained on this Common Solver options page. And if you have any questions, I would definitely recommend you look through the output controls on this page. So ordinary differential equations are one very simple, deterministic type of modeling tool. What we want to get to next are what are some other things you can make use of. So one nice thing to use is a stochastic differential equation. So let me bring over my tool for that. So here what we've done so far is we've done a ordinary differential equation where we say that dx dt goes like this equation, dy dt goes like this equation. And what we did was we said we can visualize the system as a vector equation, right? So instead of just having this right-hand side written out, we can say that f is this vector of equations. We can write u as this vector system. And so now this is the general ODE form, right? And so the differential equation library takes in this general ODE form. Now, if we want to add randomness to our simulations, we can utilize a stochastic differential equation. And the way that you do that is you can say, I have these Brownian motion terms as part of my model. So dx has a deterministic change, like the Loewi-Volterra equation, and a change that has some randomness in it. So while this dt you can think of it as like a delta t term, this is a random number whose standard deviation is delta t. So we can utilize this term to be able to add this randomness here. And now normally this term is given by a vector. The term over here is given by a matrix that is multiplied by the vector of du1 and du2. So here we see that we can utilize a diagonal matrix against du1, du2 to be able to recover this matrix, this function form. And so this is why we call this the diagonal matrix form. Right, so by default, if you don't tell differential equations.jl how you want to represent your noise, it defaults to doing the diagonal form where you have a matrix, where you have a noise term for each of your equations. So you can just write down the diagonal terms. What does that look like? Well, we can say I want to now make a stochastic differential equation. So I want to add multiplicative noise, dupt, oops. And I want to, for example, say du of 1 equals 0.3. Let me just copy this down here. I want to make this multiplicative noise, so I want the amount of randomness to be proportional to the amount of rabbits. And I want the amount of randomness here to be proportional to the amount of wolves.
Chris, as you're writing these functions down, there's a question on what the bang is for and why you put a bang in Lotka-Volterra and why you're putting a bang now.
Yeah, so there's a convention throughout Julia that if you have a function that's modifying an input, then you put this bang here to tell the users or tell other people that you're performing this modification. So the way that this differential equation solver is working in this context, to be able to define it in a way that is efficient, is you don't actually return anything. This differential equation solver is not returning its values, it's modifying the values of this existing array, so that way it reduces the number of allocations. If you're familiar with C or Fortran, this is what's done in those very high efficient libraries, And differential equations.jl follows that format to be able to get the most performance. And so yeah, this bang on different things, that just tells you that it's modifying the array. So for example, if we do something like a equals 0.5, we can notice that something like push in the Julia standard library will modify a and add a value to it. So for example, if I push into a there, and I look at the new value of a, I will have modified that array to add 0.6 to this array. Right, so this modification, this mutation, it's not required. It's just a convention, but it's a nice convention to tell people that you're changing their input. So here I'm going to make use of the multiplicative noise. I'm going to define this stochastic differential equation in such a way that I add multiplicative noise to it. And now I'm going to solve equals solve the problem. Right, and now we're being major problem solvers, and it's churning through this, well, mostly compilation here on this stochastic differential equation system. It's going to pick its own way of its own differential equation solver, and then we can plot this, right? And the way, remember that the way to understand this is that this equation right here is the first term of the diagonal of the G matrix. This term right here is the second term of the diagonal of the G matrix. And every time we solve this now, we get a different solution of the differential equation. Right? And if you want to follow along for other examples for solving stochastic differential equations, adding randomness to your models, please check out the stochastic differential equation tutorial. Now, one of the things that you might want to make use of when you solve stochastic differential equations, because they have a random output, is you might want to look at a summary over many trajectories. So you can create something called an ensemble problem, which so an ensemble problem encapsulates this problem along with, for example, ways to be able to say, you can give it a prob func that tells it how to change its parameters, change the initial condition. And so you can create this ensemble of different solves that you then want to do. And then when you solve the ensemble problem, you don't just solve it for one trajectory, but you solve it for many different trajectories. So here I want to say, solve this for 1,000 trajectories. And by default, this will actually multi-thread and solve this fast and parallel. Though you can be more explicit, and you can say, use SOSRI, the stiffness aware integrator for SDEs, and then also make use of ensemble threads. Now, I hope that utilizing all threads at the same time will not crash my Zoom. Let's cross our fingers and hope that it doesn't. And it will solve all these. So my computer is going to kick up and it's going to use all of the different threads. The first time, of course, it'll have to do the compilation, and then it will. Then you can plot all of these together. So if you plot the ensemble, it should plot all of the 1,000 different trajectories all at the same time. And one way to be able to then make use of this and plot something that's nicer than this somewhat messy, only a little bit messy formulation is to look at the quantiles, right? So we can say, I want my summary to be this ensemble summary of my ensemble solution, and it'll generate this summary, which we can then plot. And here now it's going to tell us, here is the mean of your equations, and here are the 95th and 5th quantiles. There are a lot of different options that are described in the library to be able to change this from means and medians to medians and things like quantiles to 95 percentiles. All these different choices you can find described inside of the documentation. So if you want more information on ensembles, then you can look at the ensemble parallelism page, which describes how do you build ensemble problems, how do you make them so that way they can change, initial conditions and change parameters, sample random parameters, and then all the different parallelism choices. So you can multi-thread, which is done by default. You can utilize distributed computing, so you can make this solve 100,000 trajectories across a cluster without doing any more work than doing add procs. You can utilize threads and clusters, and you can utilize GPUs automatically. So all of these do not require that you change your code at all. It just takes your existing code and parallelizes it across the different trajectories. One of the last things I want to show here before we get back is I want to show delay differential equation modeling. So one of the weird assumptions in this Lotka-Volterra equation is that the rate at which the rabbits are increasing are due to the number of rabbits right now, right? Rabbits procreate in a way such that they don't give birth instantly, right? They procreate, and then later they will give birth. And so there's a delay between when the rabbit is going to be, the number of rabbits that are, the amount of growth happening right now is not due to the number of rabbits right now, but it's actually due to the number of rabbits in the near past. So we can utilize delay differential equations to be able to encapsulate this idea. So we can have this history function in there, and we can do something like, say, h of t minus 1, or we can have tau be our delay. So we can say our delay is of length time 1. And what we want to do is we want to grab the first index of the delay. So that would be let's use a clock. So the clock rabbit. So this is the delayed version. So this is get the value at t minus 1 and grab the first one. So this is the delayed rabbit. What we want to do now is we want to use the delayed rabbits to be able to influence our current rabbit's growth. So here now what we want to do is it looks very similar to an ODE problem, except now we have to tell it, well, we don't need just an initial condition. At time equals 0, we have to tell it what this delayed rabbit should be, right? Because it's delayed into the past. So now we have to give it this history function. So h of p, oh, sorry, I need to give parameters here. H of pt. So you can see that using something like Juno is very nice because it gave me this pop-up that told me it should be pt. So h of pt, it should be giving me what I want this my pre-initial condition. So in the past, I'm going to say that there was harmony and rabbits and wolves stayed at a constant value of 1.0 and 1.0. And for the specific dispatch I'm using, I'm going to need to define what happens when I have IDXs equal to 1. And then I'm going to say that just return 1.0. Right, so this is my prehistory, so that way I can check what happens at history equals 0.5 with my parameters. And you can see that it's going to tell me that, yeah, you get this value of 1. So now I can define this delay differential equation. So my delay differential equation with a constant lag equal to tau. Now I have a DDE problem. And so this is now a differential equation that is encoding this idea that the amount of change happening right now is dependent on the past. And then I can solve this problem. So solution could solve the problem. And now the way that this delay differential equation integrator works is actually compiles the ODE onto itself to be able to generate the ODE function. So now what it's saying is that it is missing, let's see here. So what it's saying here is that my history function is missing a dispatch where, oh, did I not define that? So this is my history function right here, and it's telling me that it's calling it on float 64, and it's not calling it with the parameters because I forgot to renew my function, right? So the way to be able to read this is the history function. So it's saying that h is calling a function of a float 64 and indexes, but it should be calling a function with float 64 and indexes. And the reason why I was calling the wrong one is, remember, I wrote it down like this first, but then I added the p, and I forgot to evaluate it. So it told me that that was what's going wrong. Now when I reevaluate that function, it should be the correct version, and it can solve. And now when I plot the solution, it should be different than my original Lotka-Volterra equation because it's not using the current values to be able to perform this, to be able to get the derivatives. It's using those delayed values. So is there any questions on this general modeling aspects? Right now would be a good time to take them.
Chris, there's a question on how the automatic stiffness detection works.
That is we can discuss that more in the chat. That's more of a technical thing. It utilizes different approximations to the same value to be able to check the difference between them. And so it's actually a somewhat free estimate. It takes one subtraction and one norm value, utilizing internal components of the ODE solver that are already computed as part of the solution. I can talk a lot more detail afterwards on that. I don't want to spend too much time on that because I'd have to pull up the mathematics to really make it make sense. So yeah, let's take that afterwards if we have any time at the end. So let's see. The other thing that I wanted to go through was, oh yeah, so now let's say that we wanted to implement population controls. So population controls would be something like whenever the amount of rabbits equals 4, let's say that this 4 actually means 4 million, then we have rabbit season, right? And we allow people to just go hunting for one day. So how would we do that kind of model inside of this framework? So what we can do is we can utilize what's known as a callback. So inside of the differential equation library, we have this event handling and callback section, which describes all these different callbacks that I'll be going through. And it has a bunch of different examples in there as well. So let's work through one of, let's add an example of this to our problem here. So what we want to do is we want to say whenever the amount of rabbits equals 4 million, or equals 4 here, right? So what I want to do is I want to say, burn rabbits. This condition happens with respect to UT integrator. So the way to be able to describe it, one of these continuous conditions, is you want it to have a zero crossing. You want to have a 0 whenever this effect happens. So here I say, whenever u of 1 is equal to 4, then what I want to do, not fire truck, real fire on the rabbit, the effect should be, well, let's pick an effect. Like, let's say everyone goes hunting and you hunt 1 million rabbits instantly. So what we would do is we would say integrator.u of 1 minus equals 1, right? So whenever u of 1 equals 4, then subtract 1 from the first component of the ODE. What we then do is we call this our callback, right? So this is going to be our continuous callback with this fire rabbit condition and the fire rabbit effect. Oops. So let's just call this fire rabbit callback. And then we can do this, for example, to our delay differential equation. So we can take the delay differential equation we had, and then we just say callback equals fire rabbit callback. And what it'll do is it'll solve it now with this callback to be able to perform this change. And this hybrid model should then be, let's see what happened there. Oh, so u of 1 never gets that high. So whenever there's too many wolves, let's make this occur. And now you can see that, oof, this is a kind of weird model. Let's instead have it kill off wolves. So whenever there's too many wolves, this is actually a nicer one. Whenever there's far too many wolves, then we'll decrease the amount of the wolf population to let the rabbits grow more. And then you can see that this is the model that we get. Whenever we hit 4, we end up going down to 3, and we can utilize this to be able to model different things like population controls. Of course, this is a very unrealistic model of ecology because you don't instantly murder 300 wolves or 1 million wolves. But this is just a quick example to showcase how you can do these kinds of hybrid modeling. So you can be able to utilize discrete components mixed with your continuous components by utilizing these callback methods. Now, one of the last things I want to show in terms of this modeling is how do you solve a differential algebraic equation or these equations with constraints. I'm actually going to pull this directly from the documentation. So let me just walk through this example here. So for the Rover equation, One way of specifying it is as this ODE, but another way of specifying it as dy dt satisfies this equation, dy dt satisfies this equation, and I have a conservation law. Let's go back to our little math panel and let's see a little bit. So I'm going to have dy dt equals minus a value plus a value, right? So this looks exactly like ODEs that we had before, except how do we incorporate this conservation law? What you do is you notice that this is just 1 times that, 1 times that, and it's 0 times dy dt. Right, so this is 0 dy dt plus 0 dy2 dt plus 0 dy3 dt plus 1, right, equals this. And we move the conservation law to the other side. And we can start to see how if we had a matrix here, right, if we had a matrix and did a matrix vector multiplication, we can write down the set of equations in terms of matrix times my derivatives equals my right-hand side. Right, where my right-hand side now has this conservation law moved to be a 0 function. Right, so now we have a singular mass matrix and we want to solve this ODE. Note that you have to have special solvers for this because in some sense, the solution to this equation is m inverse f of u, and solve this ODE, but you can't actually do this because m is not invertible. And so we have a lot of special techniques in differential equations.jl to be able to handle these conservation laws and be able to make use of them with automatic differentiation and with our scientific machine learning components. So, what we're looking at here in the documentation, I guess I won't run through it because I've taken a little bit more time here than I thought. This describes how to be able to specify a mass matrix, add it to your ODE function, and use that to be able to solve equations with conservation laws. So that describes a lot of these tools throughout Julia for solving, for writing down these models with stochasticity, with delays, with discretizations. I want to point out that the way that this works, the way that this interface works, is that everyone just writes different packages and then adds algorithms to these dispatches and just conforms to the common interface. And so there's many different packages that you can choose from for this. So ordinary diffeq.jl is the workhorse. This is one that, in a lot of cases, benchmarks as the fastest, but there's a lot of other cases that we have optimized for different scenarios. So CDOD BDF is a great stiff ODE solver. It is very flexible and it handles even the equations where it doesn't do well, it still does very well, if that makes sense. ODE interface diffeq has, for example, something called RADL, which is really great for very low tolerances. LSODA.jl is very good all around for smaller ODEs. This, for example, is ran by Romain Veltz. There's even some new ones. So some researchers in symplectic methods have recently created the 16th order symplectic method, which is really good for physical problems at low tolerances. They have a JuliaCon poster. Please check out this poster and utilize this method where appropriate. Taylor integration.jl utilizes a Taylor integration technique, which is good at low tolerances and it can give automatic error bounds. Neural PDE.jl utilizes physics-informed neural networks to solve the ODE, and there's 2 different talks that are going to be about this. One lightning talk by a Google Coding student. So this shows that these tools are accessible for even high schoolers to be able to work on. And then also there's a talk in the mini symposium on partial differential equations on neural PDE.jl. There's also this geometric integrators diffeq.jl, which is a really great fixed time set library, which has a lot of symplectic integrators. If you happen to have a quantum computer around and you want to take your existing code and compile it for quantum computers, then you can use qdifeq.jl, which will be able to, it has these quantum algorithms and can output QASM. And one of the newest ones that is coming online, this one is not quite ready yet, is timemachine.jl, which is part of CLIMA, the Climate Machine Project, which has a priori time-stepping methods, which are really good for MPI, large timescale problems. If you want to have help writing your model from scratch, you can utilize tools like modeling toolkit.jl. And so there will be a whole talk at JuliaCon this year about how that can allow for automatic parallelization. You can utilize catalyst.jl for chemical reaction networks. You can utilize petri.jl. A lot of these different methods are shown in this nice GitHub repository at epirecipes.sar Julia, which utilizes the same model, so the SAR model, with a lot of these different modeling packages to show how you can use all of them. Networkdynamics.jl is a great way to be able to specify a graph and make the ordinary differential equation work on that graph. And there's going to be a JuliaCon talk on that. Power simulations dynamics is all about dynamics of power grids and for example smart grids. And there's a JuliaCon talk on this. JuSDL is a console modeling framework, which is a lot like something like Simulink. And there will be a JuliaCon talk describing this. So I'd highly recommend that you don't just utilize the SciML tools, utilize the tools from the greater Julia ecosystem that all integrate with the SciML tools to be able to quickly build these large-scale realistic models. So really just check out all of these different tools, and a lot of them will be mentioned here at this JuliaCon. So that's how you do modeling, right? So
Chris,
now
there's one question on modeling, or not really on modeling, but with the ensemble threads thing, is there an option to automatically compute, let's say, mean squared error for the entire ensemble, or do you have to write that function yourself?
Yeah, so you can, so the ensemble itself, right? So this ensemble itself, it holds itself as an ensemble solution, which is one of these vectors of arrays. If you can easily do things like array of solution to turn this into a matrix and utilize that in loss functions. Right. One of the examples that we might get to is utilizing this to be able to fit a stochastic differential equation, where you can just do things like mean of the solution along the third dimension to be able to get what the mean is at every point in time and things like that. So this is all described in the parts of the documentation on the ensemble modeling. We can write more tutorials if you feel like we need more. But in general, there's anything that can work with an array in Julia. This thing will act enough like an array such that you can utilize those analysis tools.
Right. Thanks.
So next on the workshop outline is introduction to some challenge and learning problems, right? So if you want to be able to continue to do scientific learning, machine learning on your own, what are some examples that you should be working with? If this was a live workshop, I'd actually have you coding and be working with you here. But because that doesn't seem to work out in this online format, let me at least point you to all these different resources. So one of the key things, especially if you're a student and you really want to learn a lot about SciML, is you can really look at our SciML tutorials. So in the SciML tutorials, so SciML-tutorials.jl, we have these workshop exercises. And these workshop exercises go from beginner, intermediate to fairly experienced. So we have problems looking at investigating sources of randomness and how different randomness models can affect for example, the originator biochemical reaction system, investigating stiffness, looking at Gillespie equations and mixing Gillespie type simulations with differential equations and performing Bayesian estimation on them, utilizing doing dosing for pharmacometric models, differential algebraic equations. All of these have these problems that you can follow along with and utilize this as a training source. So if you're very curious and you want to really dig in and try some things, here are some things you can try. Also, if you're an educator and you're looking for some problems that also have some solutions around, these problems are very good for you to be able to say, hey, here's the Brusselator system of partial differential equations, and here's a full description of the problem. And if you need solutions, some of these have posted solutions, some of them do not. And you can then look at these solutions to make sure that you're understanding correctly and solving these well. So if you want a whole bunch of materials, these workshop notes are probably a very good source for doing things like how do you do symbolic changes and then simulate the symbolically changed form. They're not fully completed yet, and so if you want to add some workshop solutions with explanations, that would be very great.
Chris, do you want to link to your course as well, 18337?
Yeah, so 18337 I think is mentioned in here. So if you want to find more of these, if you want to understand more about how these tools are made and how to work on these tools, you can also look at in the documentation section. There are external tutorials and teaching materials also mentioned I run a whole course at MIT all about scientific machine learning. How do you go through to do the model discovery, and how do you write all those components from scratch? There is a computational thinking course at MIT as well, which is all about how to do pandemic modeling, and it utilizes some SciML tools. And so there's a lot of these other tutorials out here. And if any other educators are utilizing our tools, please let us know, and we can add your links here. And this is just in our documentation page. So please check out our exercises and solutions. I wish we could have done this in person, but now you can do this on your own and talk to us in the chat rooms for these. It goes over everything from building models to doing performance optimization, parameter inference, and neural ODEs. Next up, we have the SciML challenge problem, which is a fully featured, here's the data set, and it has a model along with it and a full description of the model. You can take this challenge problem and then you can say, well, what happens if you do equation discovery? And you can use this as a starting point to try out new techniques, try out new methodologies, and just to understand how people make use of these tools. So we have this in full with the data and all the models and all the scientific machine learning done here. The final solution is not perfect. We're missing a lot of features like deadband, and so we encourage you to give this a try and try to see if you can find more missing physical components for us to be able to test with our laboratory helicopter. And so someone has actually asked for the schemata for this laboratory helicopter. I think we will post this online so you can build it on your own if you want. And you can then understand how adding these different components, adding voltages to these different rotaries can affect the pitch and yaw and predict its outputs. So you can check out this whole description of the challenge problem on your own. The new challenge problem that we are going to be launching today is the magnetic navigation challenge problem. So while the helicopter one is more of a good teaching problem and more of a good just basic research problem, this magnetic navigation one is a much more in-depth problem. So what we have here is we have a lot of data from these flights that are magnetometers, and what it's trying to do is it's trying to use this information to be able to perform navigation without GPS, utilizing just the Earth's crustal magnetic field. A full description of what's going on with that is in this newly released archive paper that describes magnetic navigation. And I'm going to take a quick break from talking here to let one of my colleagues describe this magnetic navigation project. I think that the sound is actually not working here. So since the sound is not working, I would highly recommend that you check out this magnetic navigation problem where
there's an option in the Zoom thing to enable streaming of sound, but you might just want to link you might just want to send this link to all the attendees instead.
Yeah. So with the place to find all the challenge problems is SciML.ai. If you look at the challenge problems, you'll see that the one on top here is a signal enhancement for magnetic navigation challenge problem, which will bring you to this repository with 3 different videos and that describe all of the data and everything that's going on here. So we have a lot of data that from test flights that are measuring the Earth's magnetic anomaly, and then utilizing this to be able to train inertial navigation systems, along with knowing truth data and knowing just the data of the magnetic fields, and then trying to use that to be able to do the full navigation. So please check out this challenge problem. If we were in person, we'd give it a try and start to work along this problem. But what we'll instead do is that after this workshop, we can give a lot of Q&A on what is going on with this data if you're interested in making use of it for your own research. So one of the nice things about the SciML ecosystem is that we don't just come with the software tools, but we also have workshop exercises, we have challenge problems, and they all come with data. So if you want to get started on doing research, you want to get straight to the state of the art, here are a few problems that you can look at if you're interested. Now what I want to get into is inference and discovery, which is what a lot of people are here for. So how do you do this automated learning of the missing components and models? Well, it all comes down to inference. Right, so let's start to do inference on these mathematical models. So let's do the let's take the lockable equations. And so here we define this ODE for the lockable equations. And remember that when we solve this equation, right, we get this plot. But a nice way to be able to look at what happens under different parameters is we can do this TMP problem equals remake our previous problem with new parameters. So P equals, so let's change our parameters to be something like 1.2, 0.8, 2.5, and 0.8. Right, so what this will do is it'll create a new problem. It'll remake this problem with the same initial condition, the same time span, but with just new parameters, right? So you can utilize these different keyword arguments like U0 equals.
So sorry to interrupt, but there were like 3 or 4 questions from attendees asking for a break. Do you have a break planned in the workshop? And if not, do you want to do a 2-minute or 3-minute break, or does that even make sense? I'm not quite sure.
Yeah, a break definitely makes sense. Yeah, so okay. I intended the break to kind of be that showing the challenge problem video. But since the sound wasn't working, I kind of went right on. But yeah, let's actually take a 2-minute break here.
Yeah, this is a good segue for a break. Yeah. All right, in the meantime, we can triage all the questions.
So yeah, Ranjan, are there any questions that you think I should look at answering?
They're all kind of specific. Oh, I guess the urgent one is, how long is the break?
Well, I guess we'll do 2 minutes. So
okay.
let's say we'll get back at 12:08.
Yeah. All right. Many of them are kind of specific. In reaction network models, how large can the integer, the stoichiometric coefficients be?
How large can the stoichiometric coefficients be? Well, so in the Rober equation that we showed here, let me get back up here. Hi again. So in the Rober equations, for example, we have an example where the equations are, the difference in magnitude, which is really the thing that's important here, is it's 10 to the 7th to 10 to the minus 2. Right, so this is something that already the coefficients are larger than the epsilon of float 32. So this is something that kind of needs float 64 to do well. We have a lot of examples of using, so the catalyst ecosystem. So a catalyst.jl is all about how do you build these large reaction networks. And these tools have ways to be able to read in systems. So you have these reaction network importers.jl that lets you read in things from BioNetGen. The way to handle SBML right now is to read it in, is to transform it to BioNetGen format and then read it in. But we plan to be able to handle SBML directly pretty soon. And then if you want to know how well different methods perform on these very large chemical reaction networks, we do have this showcase inside of our benchmarks, where here, for example, is a benchmark of a 1,122 ODE system for highly stiff chemical reactions, where there's 24,000 different reaction terms. And you can see that, for example, KenCarp4 is a method that you might want to be using over CVOD BDF and DRBDF, just because it tends to do very well on these types of very large chemical reaction networks. So those are a few things to check out. So reaction network importers, catalyst.jl, and then some of the benchmarks. A lot of them deal with these chemical reaction networks.
Right. Next question. Do you have a link to the documentation for delayed stochastic differential equations?
So the documentation does not exist for the delayed stochastic differential equations yet. I know that some people have found that we have recently posted a paper on that. So we do have this library on stochastic delay DiffEq, where we did showcase that we have everything working, they converge. It doesn't live up to the standard that we normally have in terms of tests. And so we want to add a lot more tests before we document it and release this to the general public. But if anyone wants to work on this, this is a really great opportunity, because for the most part, they already work. It just needs a lot more validation on, well, the validations have been done in a way that are not automatic. So it needs a lot more automatic testing before I would feel comfortable releasing it to the general public. But yeah, and we also just need some documentation written on it. So if you want to take a look at the library and then just, you know, or discuss with us how this works, we can get some documentation written up for this. It's just about ready. It just needs a little bit of help.
Right. Sorry for running through all the questions, but next question. If you have discrete callbacks in your continuous model, right? Does it mess up the training when you're training with neural ODEs and, you know, let's say doing SInDy or something like that?
Yeah, so currently adjoint methods cannot work with the callbacks, right? So if you want to utilize callbacks inside of the training mechanisms, you just need to make sure you make use of the differentiable programming techniques. So for diff sensitivity and things like for diff sensitivity, reverse diff adjoint, these types of methods that differentiate through the solvers, those are the ones that are compatible with the callbacks. We have some work in progress to be able to make all the adjoints compatible with it just by wrapping the callbacks in a specific way, but that's not ready yet. So we would say, so we'll be getting into in the inference portion, how do you change which method you're using for calculating the gradients, and I'll make note of which ones to utilize with callbacks. Yeah.
Yeah, I guess break time is over then. I guess we should continue.
Let's jump right into model inference then. So, we'll get into which packages can be used for inference as well. But let's just start to do some inference. So here I have a model where I solve the Lockable-Volterra equations with the parameters here. Now I can create a new problem where I just change the parameters and I solve my temporary problem to give a temporary solution. And the solution there is a bit different. Right? When you change parameters, you get a different solution. So what we want to do is we now want to say, if I have data and I have a model that I want to fit to my data, how would I find the right parameters to be able to fit to this model? Right? So first of all, let's just create a ground truth data set. So here, let's take our original problem where we say, we know that the correct parameters here are 1.5, 1.0, 3.0, and 1.0. Right? So let's create a data set. Easiest way to do this is if we turn the solution into an array. So now remember that the reason why we have 25 steps here is because this was due to adaptive time stepping. If we want to make sure that our data set is at specific points, we should probably use say that to be able to say, let's make sure we have a time series data where we have points at every 0.1 time points. So this will give us a matrix of these data points. And we can add this to our previous plot. So we can say, here's my data set. And we can then do something like do a scatter plot. So we can add this scatter plot of what are my time points and what are the data set points. You do need to transpose this because the data set is doing time in rows by default, and the plotting library does time in columns by default. And so we just needed to put a transpose there. But you can see that we've now turned our continuous ODE solution into these discrete points, which is now our data set. So this is our data. What I want to do is say, if I had the wrong parameters, how do I find the right parameters? Right, and so to do this, we would basically do this approach where we say, I would solve with this differential equation with, the wrong parameters, and I would check it against my data points, and then I'd say, well, what's the difference at each point in time, right? How far away am I from the true solution? The further you are from the true solution, the worse your estimate's going to be, and that means that you need to change your parameters more. So our loss function is just going to be solve with new parameters and then check the difference. So here I'm going to say my function is a loss with respect to parameters, or what I do is I make a new problem with this loss function. I then solve with this temporary problem, and now I just need to define some loss between my data and my temporary solution. So here what I want to do is I'm going to say, well, let's turn this into a matrix, and then let's do the difference between this and my data set. And then I'm going to do the sum squared error. So sum of apps2 of these two data sets, right? My data set generated with the new parameters against my data set generated with the true parameters. What I want to do is I want to see if I can recover this, these parameters. So now what I want to do is I want to bring in diffeqflux, right? So this example actually mirrors, if you go to diffeqflux.sciml.ai, you'll see that this first tutorial is optimization on an ordinary differential equation with a walkable Terry equation. And so we're kind of doing the same example here. And so, actually, yeah. What we do is we want to make use of the SciML train method, which is in diffeqflux. And what we do is we give it this loss function. So for example, loss. We need to choose an optimization package. So here I'm going to pull an optim for this. And I want to say, let's use BFGS to be able to optimize these parameters. And my initial parameters, let's say my initial guess is P init equals to. So I say, from these parameters, with this loss function, use this optimizer to give me the correct parameters. And this should run, and it should be able to, oh, so does anyone see what the error is here? Well, the error is that, remember that when you're using adaptive time stepping here, we don't necessarily get the same amount of time points as our data set, right? So this dimension mismatch is telling us that it is doing a subtraction between something that is size 2 and 23 versus something that's size 2 and 101, right? 2 and 23 is our temporary one, and 2 and 101 is our data set. So we need to make sure that we utilize the same save at here, so that way we always generate 101 points. If we do that, then we will be able to calculate this loss function, and we can optimize this loss to give us the result. So what it will do here is sometimes when it chooses parameters, it will choose parameters where you get blow up, or you go, a lot of this parameter space is not well behaved. And so it'll throw you these warnings sometimes of saying like, oh, there are certain areas where this parameter is not well behaved. And every time it does this, it'll reject those parameters. If we do want to turn that off, you can do verbose equals false, but it's also just like a nice indication of what's going on in the training. So it's choosing a bunch of different parameters, and it's using the gradients from those to be able to then find what parameters do well. And here it finds, so it started from 1.2, 0.8, 2.5, and 0.8. And it finds a final objective function value of essentially 0, where the final parameters are going to be what you can take as res.minimizer, which is 1.5, 1.0, 3.0, and 1, right? What were our original parameters? Our original parameters were 1.5, 1.0, 3.0, and 1.0, right? So now let's take a step back though. So this is generally how, if we have a scientific model, you probably want to use something like the FGS to fit it. But let's look at the fitting process to see what happened. A nice way to be able to do this is to utilize the machine learning libraries actually. So here we can utilize Flux, and it has this optimizer such as Atom, which do more step-by-step. So BFGS is kind of doing an inverse Hessian approximation and a line search in there. So it's not as easy to read, whereas Atom really is just doing steps by steps by steps. We can put a callback in here. So we can do something like plot callback. So let's do plot callback is a function of, it's always going to take in your parameters, and it's then going to take whatever your return is here. So here what I want to do is I want to change my loss function to return something. So that way I have my loss and my solution in here. And now what I do inside of the callback is I tell it what I want it to do between different solves. So I'm going to tell it false. So if you make it true, then that means whenever a callback returns true, it'll cut the optimization early. So you can use this to be able to say, cut your optimization when your loss gets to 1e minus 6 or whatever you need. What I want to do first is I just want to say, here, let's just take our loss. So our loss function shows up as the first thing after the parameters. Let's take our loss, and let's plot it each time as we do this optimization. And so we say that CV equals plot callback. And for now, when you're utilizing one of these optimizers from the neural network library, you have to tell it how many iterations you want to run it for. So for example, max iters equals 100. And then here it's going to, let me clear my screen. So there I did Control J, Control C to clear my screen. And here's what it looks like when I run this. So it says, oh, here's my loss at each point. And if I run this for a while, it should be decreasing all the way down to 0. Now, if we want to really look at this fitting process, we can look at, for example, what does the plot look like, right? So we can do something like plot my temporary callback or temporary solution, and then I can scatter plot the solution t against the data set. Because this is in the context of a function, I do need to make sure I explicitly display this. So I'm going to say that my figure is this. I'm going to modify my figure to add in the scatter plot. Then I'm going to display my figure. By default, everything that you do in Julia in the REPL or in the global scope automatically calls display. That's what all these things are. But inside of a function, it doesn't automatically do that. So we do have to tell it inside of here to plot. So we'll see what happens when that happens. And here we should be creating a let me look at this really quick. Oh yeah, so it might be easier just to say let's create this temporary solution in here utilizing this P. That might be an easier way to handle this. And so here now I have an animation happening live where it's trying to fit the data. It's trying to find the parameters that will then fit this to the data to then be able to give you a good approximation to the data from the model that you had on hand. Let's start that from the beginning again if you missed it. So 1, 2, 3. So if there it starts out pretty bad, but then it keeps on pushing around the parameters until it finds the parameters that will fit the data well. Right? And the loss just keeps on decreasing here. Now, for a lot of models, it is not sufficient to use a local optimizer, right? Because a lot of models have very bad local minima. So it is really nice to be able to make use of different packages there. And if you look at the DiffyQ Flux documentation for the SciML train function, you'll see that it mixes with flux.jl, optim.jl, also things like blackbox optim, NLOpt, and evolutionary. So that way you can have genetic algorithms and so you have genetic algorithms, and then you also have things like differential evolution methods. So here I'm actually going to pull in using BDO for blackbox optim, or using blackbox optim. And so now all I need to do is I just change my optimization function to BDO, and now it's going to do a global optimization, so it's robust to local minima. And I want to then, now what I want to do here is I'm just going to say BBO requires that you give it the lower bounds. And so I'm going to say my lower bounds on all my parameters are 0.5, 1's a 4, and my upper bounds are 4.0, 1's a 4. So basically I just say every parameter can be between 0.5 and 4.0. Give me what the solution is in this global space. And then it'll run this global optimization. And it'll tell you that the best parameters that it found in this space was 1.5, 1.0, 3.0, and 1.0. Right, so you can switch all to genetic algorithms and stuff with pretty much minimal code changes. Because we're running later on time than I expected, I'm not going to do the stochastic differential equation inference example. I'm going to move right on to Bayesian inference. So for this next tutorial, if you want to be able to reference it in the near future, if you go to Turing.ml, Turing.ml is a Bayesian inference and probabilistic programming language for the Julia programming language. And basically, you can define models in this which utilize anything that is a Julia program that you can differentiate through. So here in the tutorials, there is this Log-Volterra example for Bayesian estimation. And so this is where you'd find this information. Just go to Turing.ml and look at the tutorials. let me run this live. Or let me at least showcase what goes on here. So here,
Chris, sorry, just a related question in the chat. Can one use gen.jl for probabilistic inference?
Yes, you could use gen.jl in the exact same way that we're demonstrating here. So I'll mention the full set of packages in a second here.
Yeah, no worries.
So yeah, so since I already had this set up, I'm not going to run it again because it's pretty loud and spits out a bunch. But so what you do is you just define your model. So this is exactly the same as doing inference before. And here, because the model is small, we're going to say use forward diff, right? So you can use forward mode automatic differentiation, reverse mode automatic differentiation, or you can utilize all the different adjoint choices, which I'll describe in a little bit. So here, all you have to do is you utilize your same exact differential equation workflow, but now in the context of the Turing model. Everything else for the differentiation, for HMC and all that is handled behind the scenes. So here what I want to do is I say my prior for my alpha is 1.3, my prior on beta is 1.2. Now, so you just give a bunch of prior distributions, and then you just tell it how to calculate predictions from your model, right? So the way to calculate predictions is you build this parameter vector, you define an ordinary differential equation, you solve the ordinary differential equation, and now you check your ordinary differential equation's predictions against the data. Right, so here what I'm doing is I'm saying the distribution for what the possible answer could be, it should be centered around my prediction, right? So my best guess is my prediction from the model. And then there's a distribution of what it also could be around. And so my data should fall under, what you want to ask for is, what is the probability of seeing my data given this distribution? And what it'll then do is it'll find out, what are the best parameters you should have, or what is the best model you should have, such that your data is most likely. So this is called maximum likelihood estimation. So we do the same thing as before, where we generated a data set from the, we generated a data set from the vert parameters that we knew, and then we just say here we want to use the nuts sampler from Turing.jl. We use this for however many steps, and we use this to be able to create what's called a chain. So a chain object is a bunch of different parameter choices. So the way that these chains work is that you have a higher chance of going towards parameters that have a higher likelihood, right? So you have a higher chance of going towards parameters that have a better fit with your data. And over time, if you run this chain for long enough, it will give you a representation, a probabilistic representation of your possible parameters. So we can actually look at this and plot our chain here. Let me remove this REPL. So I can plot my chain, and you can see that we can now get a probabilistic fit of our parameters. And you can see that it very quickly, so during the burn-in phase, it actually kind of finds where it should be going, and it does a random walk somewhat around where optimal parameters should be. And then this gives us a distributional fit, which says that the most likely parameters are definitely really close to 1.5, 1.0, 3.0, and 1.0. Right? And you can run this longer to be able to get tighter and tighter distributions. And so this is a nice way to be able to incorporate randomness into your parameter estimates, especially if you have noise in your model. In the same way, since Gen integrates with the Julia programming language as well in its dynamical mode, you can utilize the differential equation solvers, this dynamical, just define them inside of that the function with Gen and utilize Gen in a very similar way. So that is just standard inference of ordinary differential equation systems. Now let's move on to the neural ordinary differential equation. So for this one, what I want to do is, let me find which notes that was going to be. Let's see. Sorry, give me 1 second here to get realigned. Ask any questions that show up.
Let me see if there's any. So for the helicopter challenge problem, is there a leaderboard or something with the latest solutions?
Yeah, so the helicopter challenge problem is more about finding the physical, equations that should be added to the equation. So it doesn't really make as much sense for having like a leaderboard, because you can definitely predict those equations like on the dot, but if it's not interpretable, then what we're looking for there is more the physical interpretation. The new one that we just launched, the MagNev one, that one, we don't have a leaderboard up, but that one is all about, can you actually make the signal enhancement work? And so this is definitely one that is more along the lines of what you traditionally think of as a challenge problem. So the helicopter one is more of a nice teaching example and just like a training problem. Whereas the magnetic navigation one will be the one that we really start to do testing between the different methods and such.
Right. Also, how does one call a spectral method for solving any of these equations?
A spectral method? So the spectral
like
methods
in DDEs.
Yeah, so the spectral methods you can find inside of a proxfun.jl. And so proxfun.jl showcases in its documentation here how you can solve an ordinary differential equation like this second order one by utilizing functions that come from spectral basis functions. So yeah, here's using periodic functions like Fourier series to solve equations. So proxfun does really well on that, and so we just point over to them for that area.
Yeah. Thanks. I'll interrupt you if there's anything else that comes up.
Yeah.
Thanks.
So now let's do the neural ordinary differential equation example. So. Yeah, so for the neural ordinary differential equation, first what we want to do is let's generate a data set that we want to fit. So here, what I'm going to do for this data set is I'm going to just choose this u cubed times a linear function as a way to be able to, so it's almost linear. It's this equation that is u times u cubed, right, in 2 dimensions. So here I generated this data set, which is ODE data, just from this equation, right? So just the same way that we did it before, for example, with Locke-Volterra. So now what I want to do is I want to say, I don't know what my differential equations are. I do know a little bit, right? So let's say I know that there's a relationship between the dynamics and the cube, and the cubic of my current state. One case where that actually shows up is in power dynamics, right? Because the power associated with wind is actually related to the cubic, the cube of the wind velocity. And so you can just say, I know that this relationship is the case. I know that the power is going to be related to my wind velocity cubed, but I don't know anything more. So find the model for me from that point, right? So what we can do is we can utilize a neural network to kind of hold on to this idea of a missing function. So let me describe what this means right here. So this is our definition of a neural network. You can either utilize the flux.jl form of a neural network, or we have a version inside of diffie flux that is very good for these specific kinds of small neural network cases. For large neural networks, you might want to use the flux one instead. So for this neural network, what we're doing is we're saying there's an arbitrary function, right? And what our arbitrary function is you cube the input, and then you run it through this neural network. So a neural network, if you've never seen them defined, what this is doing is it'll have 2 values, x, which we'll then multiply by a matrix and add a vector to, and then we'll apply tan h. Okay, so that's what this function is right here. Then it just has a nice way of then grabbing what these parameters are. Now what we'll do next is then we'll multiply it by a w2, right? Just like we're getting a job. And then we're going to have a b2 here. Right, so this function right here, where we first cube the input, this is our neural network actually. So this is it written out by hand. This is it written out in the framework, where it generates all the equations and does a lot of nice things for you. But it's actually just a mathematical function. So remember, a neural network is just a mathematical function with parameters in the right places, such that it can approximate any possible function if it's large enough. By just changing these parameter values around. So here is my fast chain. And what I want to do now is I want to define a ordinary differential equation by this neural network. So what I'm going to do is I'm going to say, I'm going to say my neural ODEF is going to be a differential equation defined by, well, it's just that all it is it's a call to, it's a call to the neural network. So whenever you want to calculate the derivative, just call my neural network to calculate that. And now what I want to do is I want to find my ODE. So let me just, so I want to say my ODE problem is going to be an ODE problem where the way that my right-hand sign is defined is now just by calling my neural network. My initial condition, I'm just going to use the real initial condition. You can also estimate the initial condition if you wanted. Now I want to use the right time span. So I'm going to write this in float 32 form. And now I want to put in the parameters. So what parameters should I use? Well, I'm going to at least grab starting parameters here. So my p init is going to be the initial params of my neural network. So it knows that, remember we had this functional form, we had a matrix multiplication and then add a vector. It knows that you're going to have 252 parameters in that in total. And if you give the neural network your current input, your current 2 values and your parameters, then it'll spit out the 2 values, that is the evaluation. So the initial params is just a nice way to be able to get the right shaped parameters for this. So this is the parameters I want to have. And I can then look at, for example, I can solve my problem with something like SID5, or actually let's just do this with the automated choice. Let's plot the solution. Let's see, Yeah, so that looks like so with the completely random parameters at the start, this is what I'm getting, but my data was let me make sure that I put these at the right time steps again. So here I'm using say that once more to make sure I line up with the time steps. And then I want to plot my solution, and then I want to put the data on there. And so my starting guess for the neural network is not so good, right? So the initial conditions are correct, but it just kind of drifts off because the initial parameters were just a random. This is literally just a random differential equation. So it just chose an ODE, and it just says, okay, here's the ODE to use, and it just wasn't the right one. So what we want to do now is finding the ODE is now equivalent to finding the 252 parameters that describe this neural network such that it matches the ODE well enough. So this is now just an inference problem, right? It's just an inference problem where we just have to utilize reverse mode AD and adjoints and things to be able to do this optimization. So it's the same steps that we did before then. So we want to just say diffq flux dot SciML train. We want our loss function. So we need to write a loss function that encapsulates this idea of fitting the values. So here what we want to do is we want to say function loss of my parameters is let's have a temporary problem where we remake our original problem and we make our new parameters be the input. And now we have now we solve this problem. Here I'm actually just going to choose an integrator I know is going to do well in this problem, but we could do this with the automated choice. I'm just kind of showing that you can do all these different common interface options that I mentioned before, like tolerances and stuff. You can utilize them in all these spots. So here I calculate a temporary solution, and what I want to do then is I want to do the mean squared or the sum squared error against the data points. So sum of abs2. I want to take this and let's just be safe. Let's just create this as an array, and I want to subtract off this from my data. Right, so if I do something like loss of p init, this should give me a scalar value that tells me how bad my solution is. So what I need to do is I need to find the parameters that make that better. And hopefully the parameters that make that better make this fit well. So here I want to do a neural ODE callback. So my callback is just going to be a function of the parameters and the loss here. And what I want to do for this callback, right? So remember this training callback lets me print things and plot things when I train. Here, what I want to do is I want to first just show the loss, just to be able to get a feel for how it's training. And what I do then is the same thing as before, right? So this is no different than doing the parameter inference that we did before. I'm going to say that I'm going to use this loss function. So this loss function with this callback. Well, this loss function with p in it, and let me just choose something like Adam, a 0.05 or something. I'll show how we can tune that in a sec. But we choose this callback that, nothing is different from what we did before. The only difference is that our parameters describe the parameters of a neural network instead of a functional form. Right. So now here, what we did was we got a log. So this is saying, once again, remember that when you use a flux optimizer, you need to specify max iters, or you have to use data that uses the data iterator. So here I'm just going to quickly specify max iters. Max iters equals 100, and hopefully this should train and spit out a bunch of losses. I'm going to Control J, Control O to open up the REPL again. I want to put the REPL down here. So what this is saying is that I forgot to return the Boolean halt. So remember that I said that the Boolean tells you whether the optimization continues or not. So it does need a Boolean here. Since I want this to just run for the full equation, I just want this to be false. Right? So is it going to halt? No, it's going to find out that it doesn't halt every time. And here I did something wrong. So let me figure out what I did wrong here. Oh, so I wasn't using the right problem, right? So I want to make sure I'm solving my temporary problem with my new parameters each time. So here we can now see that the loss is decreasing, and then we get to a better and better solution. As before, we can instrument this to be able to look at what's happening. So we can, for example, I'm just going to quickly here, just make a new plot of the temporary solution. And then I'm going to do a scatter of the data. And so here I'm going to do my figure equals this. I'm going to add to the figure, and then I'm going to do my ODE data. And so this should create an animation of the fitting process. Oh, I forgot to display my figure. So hopefully doing all this live and off the cuff really helps you figure out how to read these error messages. That's kind of why I wanted to do it this way. So here it is doing this in an odd way because what is my ODE data now? Oh, because I did not give it the right time points. Right, so it plotted at time equals 1, time equals 2, etc., which is not what I wanted. I wanted it to use the t-steps here. So here now I fix my callback, and now here I see it doing this. And then what it will do is it'll keep on moving until it finds the right function for that. So here, let me throw this up to 500 iterations, and you'll see how fast these things do fit before we start to optimize it. So we'll optimize this in a second. Right, so what it's done then is it has a purely parametric way, like a purely non-model way to be able to represent this ODE and then be able to figure out what the ODE right-hand side should be. So one of the ways that we found that is very good for making this fit fast is to pre-start with Atom and then run BFGS for a bit. Let me kind of showcase this methodology. So what we can do is we can have the result of our optimization be here, and then we can feed in this result to the second optimization, which uses a different optimizer. So we can start with Atom and then move to BFGS. And I usually like to set the initial start norm a little bit smaller, initial step norm. So what I just did here is I say, start with Atom. The reason why we do this is because Atom is very good at finding local minima. It is not very good at finishing local minima, right? Like it's in this spot for quite a while. Quasi-Newton methods are much faster at finishing. And so what we can do is we can do something like do 100 iterations of Atom, and then we can just use BFGS, which will run until it figures out that the solution is fit. So here I'm going to fit with Atom to be able to get this result. Then I'll use the parameters from that first optimization as the pre-start for my second optimization. And so BFGS does not run in like the same manner. It's doing a line search to be able to do essentially better stepping. It will fall into local minima if you start directly with it. I'll show that in a second, but it is much better at finalizing the optimization. So if we really want to have a nice fit, dependent on the amount of noise that we have, we can fit it, and then we can also utilize the callback to be able to say, hey, we should cut early. So BFGS is a really nice way to do this step if you don't have randomness. So BFGS does require that your loss function is deterministic. If you're using a stochastic differential equation, or if you're using mini batching, for example, then you cannot use the BFGS, which is why it's not as used as much in standard machine learning. But in scientific machine learning, one of the nice properties of BFGS is that it's much better suited for highly ill-conditioned problems, so problems that have very stiff equations. We found BFGS will work, but things like Atom will not. So now let's start to optimize this workflow a little bit. So how optimal was this? Well, what I want to point out in a sec here, or first, is you need to really watch out for how much you're printing, because so if we time this, let's get a timing for our ODE. So that took about 5 seconds to fit. And then we finalized it with BFGS. And this will go all the way to what it finds as the minimum. So the way that BFGS stops by default is it looks for whether these convergence criteria are happen, right? So BFGS always looks for convergence criteria, whereas Atom just goes for a fixed number of iterations. So this took about 14 seconds. Now there's a few things that we can do to optimize this quite a bit. So the first thing that we can do is, if you actually turn off some of this plotting and such, let's actually look at how fast that goes. Now we're down to 1 second, 1.5 seconds. So more of the story there is that these computations can be fast enough that you don't want to, you maybe not reuse the computations, but the biggest thing is actually building figures fast is actually a much more impact than you might think. And then we can also see this on BFGS to a lesser extent. So now let's go to our loss function. So one of the keys to really optimizing this is choosing different methods for doing the gradient calculation. So if we do the loss function calculation, so at time loss of p init, you'll see that the loss function is almost instant. So where most of the time is happening is in the gradient calculation. The gradient calculation is really the key to all these tools. So if you want to read up more on all the information on this gradient calculation, you'll want to look at the choices, controlling the choices of adjoint page. This is in diffeqflux.sciml.ai, controlling the adjoints. So differentialequations.jl has a very extensive system for doing adjoint sensitivity analysis, where if you have a solution, if you have a solve, and then you do zygo.gradient over it, or you do tracker.gradient, or you do reverse diff.gradient, all of these different machine learning or differentiation libraries, it'll take control of what the actual calculation is and utilize what it calls as a sense algorithm to be able to compute the derivatives that the automatic differentiation library is asking for. So by default, right, so when you're using Turing.jl, when you're using zygo.jl, when you're using flux.jl, all these different packages, by default, we're actually taking control of how the gradient calculations are working, which is why it just works naturally with just the standard syntax. And now you might want to ask a question, well, what are all the different choices I have here for sense algorithms? And this is what I really was describing earlier in that presentation as there are different things that you might want to make use of in different scenarios for mixing speed and accuracy. So there's a whole different combination of choices. Together, there are 1, 2, 3, 4, 5, 6, 7. This one isn't so great. So there's more, just 7 different sensitivity algorithm choices. And then there's a bunch of different combinations of them. So for example, you can utilize interpolating adjoints. So you can say, I'm going to use this forward mode interpolation. And the way that I'm going to do the internal vector Jacobian products is going to be tracker, zygote, or reverse diff. And so there's all these different combinations of these different automatic differentiation tools that will use them in specific ways to be able to calculate this fast or slow. Because there are so many combinations, right? There's a combination of at least 3 choices here, well, with numerical and forward mode as well. So at least 5 choices with, you're getting into, 30 choices for these. So one of the ways to be able to understand what to use is this choosing the sensitivity algorithm section. The moral of the story, though, the quickest thing to understand is that if you have less than 100 parameters, then forward diff sensitivity or forward sensitivity, which is these forward mode automatic differentiation methods, are the fastest. Once you get above about 100 parameters, then we see that you want to utilize something that is a reverse mode method. Now, there are many different of these different adjoints. So quadrature adjoint tends to be the fastest adjoint for smaller ODE systems. So when you have something around that 100 parameter range, quadrature adjoint does very well. Backsolve adjoint is this one that is, if your problem is very non-stiff, it can work. And it will be the fastest if your problem is very non-stiff. But if your problem has just a little bit of stiffness, it can give a lot of accuracy issues. You can mix this with checkpointing to be able to fix that up, though, and I'll describe that in a second. Interpolating adjoint is kind of this middle ground, which generally works even on black box equations and these kinds of things, and it has checkpointing to control memory use. So it's kind of in the middle between something that uses a lot of memory for high accuracy and something that utilizes almost no memory but has some stiffness issues. This one is able to handle stiffness, it's able to handle non-reversibility, and it's able to also not use as much memory as quadrature adjoint.
Chris, one question.
Yes.
When you're writing these scripts, you use a lot of global variables, right? Because you're writing a script, and then in the loss function, you're using, there's a global variable involved in calculating the loss. So does this impact performance in any way?
Not really. I mean, you can do things like you can make a functor to be able to make this more concretely typed. In general, most of the function calculation is inside of the solve call. And so you generally have a function barrier there, right? So other people in this JuliaCon will describe things like function barriers, which means in the context of this solve, everything is concretely typed anyways. And so you don't need to worry too much about what's going on the outside.
Just to add to that, I mean, it's still a good Julia practice in general, but in some cases it makes a difference. In some cases it doesn't.
Yeah, in some cases it'll make a difference. What you really do need to make note of is that your ODE function, so like this neural network, or your ODE function like the Lockable-Volterra equations here, these need to be very well concretely typed, because these functions will be called over and over and over. And a lot of good performance really comes from making sure you do those well. I have a talk, which we'll be showcasing at this JuliaCon, for if you give us a bad version of this, we can automatically compile a faster version of it and automatically parallelize it. This is the talk, Automatic Optimization and Parallelism in Differential Equations.jl. So we'll describe, if you're too lazy, you can utilize things like auto-optimize.jl to optimize this.
So one more question on how do you avoid overfitting?
How do you avoid overfitting? Yeah, so there's many different techniques for doing that. One thing that you can do is mini batching, right? So instead of using all of your data all at once, you can utilize one of these tutorials. Like, so if you go to the DiffEq Flux tutorial, there is a very nice tutorial here on something like, so I think the MNIST tutorial actually has mini batching in there. So this one shows how to use GPUs and the MNIST data set along with Flux's data loader to do mini batching. That's one really nice way to make to do that. Another way to do it is to just use this callback function, right? Instead of just always putting false, you can make it cut out early, so that way it it just doesn't try to go way too far. Another thing that you can do to be able to decrease the amount of overfitting is to utilize a stochastic model. So if you think about it, a stochastic model is always injecting a little bit of randomness. And so it's trying to make sure that you're getting the gist robustly fit instead of trying to fit the very specifics of a data set. And so utilizing additive noise stochastic differential equations is actually a very classic way to avoid overfitting in the differential equation literature.
Sorry, just one more on that, just because I've tried to train a bunch of these things. One, just from the modeler's perspective, I think one way to avoid overfitting is try to start off with as small a neural network as possible, because you're not really getting anything from the overparameterization. It makes the neural ODE hard to solve and hard to train, and you don't really get too much of a benefit. So, try to start small and then get more and more ambitious as you fit the.
Yeah. And one of the things here too is I'll be showing it in a second, is that you can get a lot more generalization by utilizing the sparsification of the neural network, right? So after you train the neural network, what I like to do is not keep it as a neural network, but actually turn it back into mathematical equations, and that helps with the generalization a lot. But yeah, I guess one other thing to demonstrate is the paper for this is not quite out yet, but we do have a technique in here that you can start using for smooth co-location. So you can take a data that could have a lot of noise in it, you can create a co-locating polynomial through that, and then you can try fitting the co-locating polynomial, or since it has a well-defined derivative, you can directly fit its derivative values. And that can be a nice way to be able to pre-train and then be able to fit in a way that does well with noisy data. So yeah, so now let's get into using some of these sensitivity algorithms. So what you do is you say sensalg equals, the default here is always going to be this interpolating adjoint. So what I'm going to be doing is I'm going to be timing against a proxy for the gradient calculation, which is just the training loop itself. So how did that do? So before it was at, let's see. Oh, so I cut out all the printing here. So let's use this as our starting point. So we have, let me do my salg equals interpolating adjoint and throw this in here. So now I'm just going to use a bunch of anonymous functions to be able to swap around what sensitivity algorithm I'm using. And so, for example, I can do something like make my loss function be the one that is now using salg equals backsolve adjoint. So here, this is the version that requires that your ODE is reversible. And if it is reversible, it tends to be pretty fast. So let's see how fast that will do. So remember that the first time it's going to compile. As you have these larger and larger equations, though, the compile tends to matter a lot less. But so this one, it didn't seem to do much of a difference in this case. So that trick right there was really just, if you have an equation which has tabbed out a lot, and then you put your next one, you see that sometimes when I'm pasting in here, Juno will throw it up here. And so if you just make it back to the beginning here, then you can paste without having that be an issue. Sebastian, if you're on, let's get that fixed. But anyways, so what we can also do is we can say internally to the adjoint calculation, we also can tell it to change the way it's doing the automatic Jacobian vector products. So we can say AutoJac_vec equals reverse diff VJP. And now this will be able to, after it compiles, it will work a lot differently. So this version of VJP is not compatible with GPUs, but in a lot of cases with CPUs, it can do better. Now you'll see that in the standard set, it will not. So once this is done compiling. And so you'll see that in the standard setup, it does not do as well. But now there's this command in here that I can use where I can say with true, where what this is doing is defined here, where it can trace through your equation. Where is that? it can trace through your equation, figure out if there's no branches, it can pre-compile a very fast version for scalar equations and all that. And so if you have a lot of scalar operations and you do not have branches in there, this reverse diff VJP true is a very good one to make use of.
Sorry, just to interrupt. Can you get a lot of statistics about the forward solution with DE stats, right? Can you see those same statistics with the adjoint?
You can. So if you want to make use of, if you want to see those statistics, you can utilize the components that we use to define our adjoint problem. So if you solve a solution forwards, you can build an adjoint sensitivity problem. And then this adjoint sensitivity problem is how you'd actually look at the solution of the backwards pass. So this is all defined in the bottom parts of the documentation. Also, you can define loss functions, which are not on the discrete values of the time points, but you can also define it on the integral of the time. And so there's a lot more you can do if you want to directly utilize the adjoint interface. What I'm showing is just the very simple high-level view with it. So you see that when we utilize backsolve adjoint with this reverse diff to VJP, we can actually get this a lot faster. And now let's see what happens when we chain that. So let's take this one, and then let's take this one, and now we utilize BFGS, where we do the initial step norm equals 0.5, and then we make this start at res.minimizer. So this one will take 1 second. This one will take, let's see. Does anyone see the typo I did here? Oh, minimizer. Let's get rid of this. So this total fitting of the neural ODE, after we do this quick optimization, we get it down to around 4 seconds. There's one last thing that we can do to get this example down to 3 seconds. I forget exactly what it is, but it was in my notes. But yeah, so if you have any questions, so the way that you'd find more information on choosing the right sensitivity analysis algorithms is in this controlling adjoints page. Remember that there are some results that showcase that you can, that utilizing the automatic differentiation forms is more stable than the adjoint forms. And so you might want to make use of reverse diff adjoint, and you might want to make use of tracker adjoint if you need to utilize, if you need a lot more stability. Otherwise, backsolve adjoint, interpolating adjoint, and quadrature adjoint are the ones that we generally gravitate towards. But you can switch between the two at any point. Now, just as a note, all 3 of these adjoints are compatible with the DAEs, except we do not recommend you use backsolve adjoint ever with DAEs. It generally has a stiffness that is inherent that will cause the reversibility to never work out. We have some contrived equations where it works, but generally it has to do with a Lyapunov coefficient that occurs when you have the singularity in the mass matrix. So you can utilize any of these adjoints and any of these automatic differentiation methods with DAEs, but we highly recommend that you use something like interpolating adjoint. And now you can also set, so what you can do with these too is you can also say things like sensitivity, you can also say like checkpointing equals true. And then what it'll do is it'll save values from the forward pass, and it'll use it in the reverse pass to be able to correct the value as it goes backwards. So backsolve will do a correcting form. Interpolating adjoint will do a form where it only interpolates smaller areas. So this can add robustness, and it can add, it can reduce the memory requirement of the fit. And so we also have these available now for stochastic differential equations. So you can utilize anything except quadrature adjoint for those. So you can use forward mode automatic differentiation, reverse mode automatic differentiation, forward sensitivity analysis, and adjoint calculations, except for quadrature adjoint. So the backsolve form and the interpolating adjoint form do exist for that. And for delay differential equations, you can do all these same techniques as ODEs and DAEs, though we do have to mention that the lag times cannot be estimated with the current methods, and we are working on adding the lag times. And just to reiterate something that was mentioned earlier, if you are utilizing callbacks, that also has a difficulty with the adjoint methods, so you want to make use of one of these discretized and optimized methods. And this is all defined in this controlling adjoints page. And if you want to look at benchmarks between different adjoint choices on a neural ODE, then you can look at this, for example. But I do want to really recognize that backsolve adjoint will be the fastest when it works, but they're in most of the cases that we demonstrate. So in all the partial differential equations, in all the stiff equations, it actually fails to reverse and it fails to get the right gradient. So you should really double check whether backsolve adjoint is appropriate for your problem before you use it. But it's a nice flip that you can always flip to and get a faster solution if it's a good one on that equation. So now what I'm going to do is I'm going to do this in that last part. So now what I want to do is I want to do one of these universal differential equation examples where we fit a small time series to be able to recover the missing equations and then extrapolate forward in time. So I'm going to instantiate a manifest actually for this one. And the place where you can find this example is if you search for universal differential equations, you can find the repository that's associated with this, with that project or with that paper, and you can find the full manifest and these examples here. I'm just going to quickly run through it. So you utilize this as the symbolic component, this data-driven diffeq. So what we want to do is we want to generate, again, a data set from a Lotka-Volterra equation. And what we want to do now is we want to utilize a neural network. So I want to utilize some known pieces of the differential equation mixed with the neural network to recover the missing terms and then be able to extrapolate into the future. So let me start by, once again, I take some form of Lotka-Volterra equations, I solve them at constant, at constant fixed saving time points. And now I'm just going to scatter plot and show what my data looks like. Let me throw this to the side here. So here, notice that what I'm using as my data is just this very short beginning at the start here. I don't want to give it too much information. I want to give the information, some scientific information. But I want to say I'm in one of these cases where I don't have very much data. Right, so I just have data on this aspect right here. So I add some noise to the data just to make sure we don't overfit. And then we just look at some noisy data. So now what I want to do is I want to define this universal differential equation, right? So the way that I define it is I define an ODE where I have a neural network be these portions, and I have ODEs, the actual terms be written in here. So here I say, I'm just working with the assumption that let's say I knew these parameters. So I know the parameters for here, I know the parameters for here, right? Because I know the reproduction rate of the rabbits and I know the competition rate of wolves. And now what I do is I have an artificial neural network that then gets added to the derivatives of these equations. And this artificial neural network is defined by one of these chains. So it's just very similar to what we did before, where what our P is going to be is the initial parameters of this neural network. So now this is very similar to what we did, except now we just have a neural network that is only for one small part of our differential equation. We can solve this and we can plot. And we can see that, let's see. We can solve this and we can plot, and we can see that this actually ends up being a somewhat good predictor on this set of equations, but it's a very poor predictor on this other set of equations. So we do the same process as before, right? So the way that we know whether our universal differential equation has good parameters or not is we perform a prediction, and then we calculate the loss of the prediction against the data, and then we would see, for example, what is our current loss? So it just needs to compile through here, and it says that I have a loss of about 60 to start, And then here, I'm also just giving it extra information. So your loss is always going to be the first value that is returned from the loss function. All of your other things are just passed on to the callback. So you can see here the callback has a prediction in there already calculated. So here what I'm going to do for my callback is I'm just going to I'm going to just create an array of the loss function so I can plot the losses later. Same thing as before. So I'm going to start with Atom before I go to BFGS. And this is actually an example where if I started with BFGS first, it would actually find the bad local minimum. So we want to bump it around with Atom first for a bit. And then after we bump it around with Atom, then what we'll do is we'll do an optimization with BFGS. And hopefully after that, we'll have a very good fitting on a neural network for the missing part of the differential equation. Actually, if I'm going to be plotting, let me leave this here. So basically what I'm going to show next is I'm going to show, what is the error in the time series on this time span from 0 to t for the trained neural network. And let's actually look at what the function it gives here, right? Because it learns to be a function. We know what that true function should be because we generated the data. So that should be a quadratic function. So we should get something where, here's the true missing term is a quadratic, and this neural network should be learned to essentially be the missing quadratic term of our model. So here we got a successful run with Atom in 47 seconds, where it gets us from a loss value of 60 to 7, and then we're going to then complete that with BFGS. It should take about a minute if I recall correctly. So while that runs, let me just go over this a little bit. So there's a lot of different packages you can use here for model inference. For example, you can, so diffie-q-flux has this interface over optim, flux, black box optim, evolutionary, and more to be able to do genetic algorithms, global optimization, also mix in neural network optimizers like Atom, and then mix in workhorses like BFGS. Data-driven diffie-q is what I'll show here in a second. We'll turn data back into equations. Bayesian optimization was done with Turing.jl. Gen.jl is another system for Bayesian estimation. And what I want to show here is that we actually have a new optimization package coming up, which is pulling together, essentially it's going to be a new interface that pulls together all of the optimization packages, all the local and global optimization packages into one interface that will also be differentiable in case you want to nest optimizations. And so because it's more than global, it's called galactic optim.jl. So this is not completely done yet. This is one of our summer projects that we should have done by the end of summer. So right now it's gone down to a loss of pretty low. Should have actually made it cut, but it usually cuts a lot quicker just because of the initial. So it is a little bit dependent on the initial conditions that you got from the neural network. And here now we saw that it finished. We can actually look at res2.minimum to be able to see that we got to a loss of like 60 minus 3. All right, so let's actually plot our losses. So our losses are, so we started at a fairly high loss, it dropped down. This is where we then switched to BFGS, where BFGS did a line search and did a movement, and then it very quickly dropped to be able to finish. And so when we now plot with the neural network on top of our data, we see that we're able to fit this quite well, or on top of the true solution, that is. Now let's look at the learned derivatives, right? So the actual value that it's spitting, so this value that here for this missing term, let's actually plot what these missing terms are. And you'll see that I actually found the correct missing terms numerically. And now what we want to do is, so those are the missing terms. And what we want to do is we want to take this very good fit for the missing part of our function and transform this back into equations. So for this, we're going to use modeling toolkit. Right, so modeling toolkit.jl is this library for symbolic numerics. right? So it has these ways of building symbolic expressions and performing some building Julia functions from symbolic expressions and sparse matrices and all that. What we want to do is we want to represent the possible functions that we can have in modeling toolkit here. So here I'm going to say that there's two variables, right? There's two inputs into my function, u1 and u2, and I'm going to build a basis of a bunch of different polynomials. Oops, I named h again somewhere else. And sorry about some of these warnings. I'm mixing an older version of the library with the newer version, but since the things in SciML generally are quite stable, you can kind of mix versions and you'll get deprecation warnings. So let me print out what the basis looks like. Yeah, so if you do a print line on the basis here, then you'll see that the possible functions that I'm looking for are linear combinations between cosines and sines and these higher order polynomials and such, because this is what I specified in this loop. I just created a whole array of all these different symbolic expressions and basically just said, let's just find out what the equation is in terms of these, let's find out what the right-hand side is in terms of these functions. So now we can create an optimizer for the SInDy problem. So this is all described in, if you go to datadriven.sciml.ai, then you'll see that there is this sparse identification of nonlinear systems. This is all described here and how you can find out equations from data. So what I'm going to do is I'm just going to choose an optimizer from there. I'm going to choose a lambda for the thresholds. And now let's look at one thing, right? So let's look at what happened if we wanted to just do pure SInDy. So if we just said, I have time series data here, I just want to recover the full differential equations with no prior information. Would that have worked, right? This is one question a lot of people ask for good reason. If you can use less prior information, it can be better if your prior information is wrong. So let's do some SInDy here. So it's going to run an optimization process. And essentially what this is doing is it's going to optimize this this right here, which is essentially a sparsification of the coefficients, and it'll return the sparse coefficients. So it'll try to give you a very sparse form that will try to match the model as well as possible. So it tries to give you the least number of equations that will then fit as good as possible. And that's what all these different parameters are for the tolerances and such. Right, so you can adjust the tolerances for what it means by how good of a fit and how much regularization. So here we see that if we only utilize our data to be able to try to find the differential equation, and we utilize no prior information, it actually does not give us the correct differential equation. It's somewhat reminiscent, but not really. It doesn't do well here. But let's do this on a different part, right? So what we did was we took the values of the differential equation along the time series, and we run them through the neural network. So what I want to do is, so L hat here is the output of the neural network, and the x's are the inputs to the neural network. And what I want to do then is I want to say how should I transform this neural network, this function from x to L hat back into a system of equations. And so what I do is I just say my inputs are all x's, my outputs are all L hat. This is the basis that I have. Any of these functions are possible. Perform an optimization and tell me what symbolic equations you should be using. And it will perform the symbolic equation, or perform the symbolic simplification just by doing the SInDy call. And remember, you have to make sure that you choose max iterers and whether to do denoising. But after we do this, what we get is, ta-da! Right. So this is like the grand reveal here. It's basically found that we fit this artificial neural network to be part of the equations. We run the SInDy here, and we actually find that the missing equations is P1 times U1 times U2, and the missing equation is P2 times U1 times U2, which is the true missing equations that would have come from the data. So now let's see how to make use of the learned equations. Oh, so I'm mixing a new and old version, so sorry about that. So what we can do is we can define a new ODE system that is utilizing this basis function in the background there. let's see. Oh, so first what we want to do is, so because we use regularization, our parameter values might not be fully correct. And so we can utilize a different form of this optimization that will be much better at finding what the correct parameter values are. Because as you know from regularization, right, this fitting is going to give an estimate that is sparsified, but also a bias sparsification. So we can reduce the bias and then do another fit. Another way we can make use of this too is that we can define the ODE that is in the sparse form and then just do the parameter inference like we showed in the first part. So now what we can do is we can pull out this, this fixed version. We can now define our new ODE system, which our ODE system will be calculate the ODE parts that we know, and then add on the parts that we found, where the parts that we found come from here and here, right? So this is our DU1 term or DU2 term. And now let's solve the ODE for the future. Oh, let's see. So those two parameters, right, are the parameters for what P1 and P2 are. So now let's solve this ODE into the future with this set of parameters. And now if we do the, now just as a double check, right, the neural network matched pretty exactly. The sparsified form isn't as exact, but it's pretty good. So now let's do, so this is a good check to be able to say, okay, we sparsified down to just a quadratic equation that matched what our neural network did very closely.
Chris, there's a question with regard to fitting this. Gabe says, I missed why this version of SInDy worked. I mean, why does fitting the neural network work better than directly trying to learn from the data?
Yeah, so if you don't know what, so one other way you can make it, that is a very good question. One other way that you can do this is you can just say, I'm just going to add all of these equations to my ordinary differential equation. Right? You can just add all of these equations directly into your ordinary differential equation and then do an L1 regularization of that fit. And then hopefully you get a lot of zero parameters. If you give it a try, I would say give it a try, and then you'll really understand why you do this. Right? One of the things I described earlier was that if you have very specific functional forms for your differential equation, it can be really ill-defined, right? So the loss function is not very smooth at some point. And so if you just actually do it in this example, where you just put all of these equations in there, you get a function, you get a starting function that has a very bad likelihood function, and it becomes very hard to fit. It's actually very difficult to fit. You need to use a global optimizer, and you need to do a lot of extra tricks. Whereas if you use a neural network, one of the key properties of neural networks is, let me see if I can actually pull that up really quickly. So neural network, local optimization, local optima is global. Okay. So yeah, so there's a bunch of papers out there that basically show that if you have large enough neural networks, it just turns out that local optima are the same as your global optima because they don't actually represent a function anymore, or they represent a function, and so their exact values don't really matter, right? You don't care what the parameter values are of the neural network, as long as it's finding the correct missing function. And there's a lot of results that show that, you know, if for large enough neural networks, you have very well behaved local properties. And so by utilizing a neural network as like a domain to move through, you can make this form of model identification be much more robust. If you want to show this to yourself, I would say after this workshop, take some of these examples, do it in this form, and do it with just the pure optimization, and you'll see why. You really have to show it to yourself. And so what I want to do now is I want to just say, here I found a set of equations. Let's run it from 0 to 50 and just see how close we get to the original equation. So our original equation was this solution right here. So our original equation, if we were to have done it longer, right, we only did the data here, but if we ran it longer, we'd get a Lock-Volterra equation like this. And if we utilize then the equations that we found, right, we only trained on data that is from here to here. But if we push it to the future and just say, instead of solving from 0 to 3, let's extrapolate it to the future, you'll see we get a very nice fit. And we can do other things like we can post-train some of these parameters to be able to improve it even more. And that's how we get this figure from this paper, where we only use training data from 0 to 3, but we still get a fit that works pretty well until time 20. And so when people tell you that neural networks do not extrapolate well, what they mean is that, once again, that is if you only use a neural network. But if you utilize a lot of other information in there, like if you utilize a lot of scientific information to be able to predefine some differential equations, and you sparsify it down to something, then you'll get less overfitting of the neural network parameters because now you have less parameters, and it tends to generalize much better. So any other questions at this point?
With regard to this, not really. There are a few underrated questions that we should probably go through at the end.
Yeah, so let me just go through my last example because this is kind of a fun one that I can do. Very little library usage here. If you're just kind of interested in scientific machine learning, this example is just a great illustrative problem that you can even do in classrooms. So for example, we have this new neural PDE.jl that I pointed to, right, where you can define your differential equation in a way that's purely symbolic, and then you just give it a neural network and it will solve the equation. But you might want to know what this library is actually doing. And I can do a simple case of this actually here live in a few minutes. So what is this library doing? Well, there's two things. The first one is the deep SDE method, which is essentially what I showed earlier. Right, so what I showed earlier as you can solve these partial differential equations by defining these stochastic differential equations with neural networks in them, and then it just becomes one of these universal SDE types of problems where you utilize our adjoints through SDEs. Right, so that's one set of what it's doing. The other thing that's doing is physics-informed neural networks. If you discretize this to physics-informed neural network, then you get a universal differential equation. If you keep it in its continuous form, then you do have to train it a little bit differently. But training it a little bit differently is something we can do just with the primitives provided by Flux. So how do you solve an ODE with a neural network? This is really the key example. So a physics-informed neural network is solving PDEs. How do you do this with just an ODE? Let's just run through a full example, start to finish. So let u prime equals f of ut, and with an initial condition. Right, so a neural network is a function approximator. We want to represent the solution to this or differential equation with our neural network. So what we will do then is we'll say, well, by definition, if our neural network is the solution to this ODE, then when we differentiate it, right, when we differentiate this neural network, it has to satisfy that f of the neural network times applied with t is these things are equal. Right, because the solution to the ordinary differential equation is defined as the function for which this is true. So if we want this to be our solution, we just say this has to be true about our neural network. And also we have to, when we plug in 0 to our neural network, we also have to get an initial condition out. So we kind of reverse this now. We say, this is what we want to be true. We want this equality and we want this equality. So what we do is we define a cost function, which is sum over a bunch of different time points. And at that time point, evaluate the neural network at t and subtract off the function f applied with the neural network at t. Now, if the neural network is truly the solution to the differential equation, this is 0. And so what we want to do is we want to find the parameters such that this is as close to 0 as possible, right? So when we get close to 0, then we'll have something that the neural network will be representative of the solution of the ODE. And so this is just now an optimization problem on a neural network, right? We define this cost function and we minimize this cost function. Now with it like this, we do have to make sure that we can satisfy the initial condition. So we could just say we take t at, we make sure that t equal to 0 is in here, and we have a term where we just say n of 0, nn of 0 minus u0 has to be equal to 0, right? So we add that to the cost. We can actually do an extra trick here. So we can say instead of using the neural network as our test function, we can instead say that we want to use g of t as our test function, where g of t is t times the neural network minus u of 0. So think about it a second why we might want to do that. And the reason why we do this is because when t equals 0, then g of t equals u0. And when t is non-zero, then we have a universal function approximator here. right? So this gives us, so if we use g of t instead, we always satisfy the initial condition. So in some sense, this is one trick to be able to input, more scientific information into our neural network. So you can do all sorts of other tricks. So there's a lot of papers out there for physics-informed neural networks where you can do things like ensure that if you're trying to make it solve Navier-Stokes equations, you can make sure that you can make sure that certain fluxes over given boundaries are always equal to 0. You can make sure that the divergence is equal to 0 by specifying specific function forms, right? So let's actually do this out in Flux right now. So here I have using Flux, and what I want to do is I want to define this neural network, right? So this neural network takes in one value, and I just put it into an array. I then run a neural network through it, and I turn it back into a scalar. So this is just my neural network. I define g of t such that it's always going to have g of 0 equal to 1, which is my initial condition. Now what I want to do is I want to solve this ODE. Let me just write it down here. U prime of t equals sine of 2 pi t. Right, so or u prime of t equals cosine of 2 pi t, right? So my function, my right-hand side, is actually just ends up being a function of t. So here what I'm going to do is, just for demonstration, I'm going to use calculate derivatives by using a finite difference, but you should use automatic differentiation in practice. So here what I'm doing is I'm saying my loss function is calculate nn prime, oops, sorry about that. Calculate nn prime and subtract f from there. So I'm going to calculate nn prime just by a finite difference or automatic differentiation. I'm going to subtract off f, and I'm going to do this at a bunch of different time points. Right, so now what I want to do is I just want to optimize. I don't know what I already assigned to data, so let me do this a bit. Now what I want to do is I want to optimize my coefficients of my neural network such that this relationship holds. And then what I want to do is I want to plot the solution. So, if u prime of t equals cosine of 2 pi t, right, then what's this analytical solution going to be? Well, then you take the integral of both sides, right? You take the integral here, you take the integral here. And so then you see that u of t, the true solution, should be equal to sine of 2 pi t divided by 2 pi, right? So here what I'm going to do now is I'm going to plot the solution of what the neural network is versus sine of 2 pi t divided by 2 pi. And there you go. Now you have a neural network that represents the solution to a differential equation, and this is the basis behind the physics-informed neural network method. So we can then take arbitrary we can take arbitrary differential equations with different derivatives, more derivatives in different directions, and just use differentiation in those different directions to be able to calculate the loss function for given terms, and that becomes the physics-informed neural network method, where we can take in a symbolic description of a PDE and generate solutions to it directly from your symbolic equation.
All right, Chris, we're at the end of the workshop. Should we answer questions and call it a day?
Yeah, so I just want to say before we answer the questions until we're done here, thank you for this, for letting me have this opportunity. I hope that this is useful for you in doing all sorts of modeling and finding of models. There are a ton of different talks at this JuliaCon that will be relevant to this type of workflow. So for example, if you want to do probabilistic optimization, so you want to do something like optimize the probability that optimize the probability that the maximum number of wolves is above 4. Then you can utilize this probabilistic optimization setup that we have with the diffeq uncertainty to be able to do this about 1,600 times faster than Monte Carlo methods. So that's going to be described for the first time actually at this talk by Adam Gerlach. So we have a very nice example by one of the students here at MIT. Raj will be talking about how we can do automated discovery of droplet fragmentation. So his master's project took about 2 years to be able to discover these equations. And then he took my IIP course. And so in 1 month, he learned how to utilize these things. And basically in a weekend found a way to be able to discover the same equations he was able to derive. So it's a very nice example that these are finding true equations on real data. Valerie does a very nice talk on exploring disease vector dynamics for environmental change, which is utilizing all these SciML tools. Some other optimization, so another modeling package is networkdynamics.jl. They've done a really great package for building a graph and putting ODEs on graphs. And then I have this talk on the last day, which will be if you have code and your code is written in a way that is not optimized, like I've done in a few cases here. Right. There are a few cases where I haven't fully optimized my code, and you can just say, well, do you want this to then be optimized for me? Give me the optimal way. And we now have these compiler-based tools that will rewrite your equations and auto-parallelize them, change which algorithms are being used. And this is our automatic optimization framework I'll be discussing on July 31st. All these feature SciML tools, this is just 5 of, I lost count of how many there are at this JuliaCon that you're utilizing SciML in there. So check out a lot of these other talks. If I didn't list you here, it's only because I ran out of space. And so really the key idea here behind the Julia SciML ecosystem is definitely utilize finite difference methods, finite element methods, pseudospectral methods, implicit ODE solvers, high order adaptive SDE solvers, utilize all of this stuff with our sparse, our sparse matrix forms, our sparse adjoints, our stiffness handling, our stuff all for ill-conditioned problems. Utilize this all together to be able to solve real, modeling problems. We'll be able to generate, and automatically discover models in cases where you have these very ill-conditioned problems. So, yeah, thank you very much. I'll just do a bunch of question answering now.
Great, thanks, Chris. Lots of comments here about everybody loving the workshop and loving your energy. All right, so first question is with regard to the pandemic model that you mentioned at the very beginning. A, is there a reference for it? And B, has it been validated? And yeah, how do you get more details on it?
Yeah, so this pandemic model is more so, this one is just a toy model. I wouldn't look into this. For this other one, data-driven quarantine strength, we just put this online yesterday. How would I find it? Maybe my tweet from yesterday is the easiest way to find it. Raj, if you can actually post this in the chat, that'd be really nice. We just put out our paper where we submitted it as well, which basically goes through, and basically what it does is it transforms time series data back to quarantine strength data. And then what the paper really does is it's all about the validation. So the paper goes through and it just says, like, in this country, we showcase that we have quarantine efficiency like this and on contact rates like this. Well, does this correspond to reality? And if we look at the data that people found on the ground for given states and given countries, then we're able to showcase that it lines up very nicely. When we see different trends in there in different regions. Actually, we put up a website here, this COVID-19 ML, which demonstrates this whole methodology. And then it has this worldwide map that has done this pre-training of all the data here. And you can download all of the generated data from this and hopefully make use of it to be able to link things like social factors to quarantine effectiveness. So this just gives us a nice way to be able to, get pretty good proxy for quarantine effectiveness from a traditional time series. So that way people can use it in different social studies. So if you want to see all the validations, that's all what's in the paper. And since we just put it up, we'd be happy to get feedback as well.
Yeah, you should. I recommend whoever asked the question to also catch Raj Dandekar, who is also giving a talk. And you can also find him on Discord. He can also give you more information. So our next question, can you use these techniques to somehow correct output across different solvers that is correct from their deviations?
Yeah, so there are some ways that people have done this. So, for example, there is a deep Euler method. Right, so the deep Euler method is this methodology where you can say, well, I have an Euler method and I have a local truncation error, and I can try to estimate the truncation term to be able to improve my solving. The only issue with this kind of methodology is it doesn't generalize very well, right? Because if you have this neural network, it has a fixed size number of values as your input. And so, and also it only trains this it basically trains how Euler is wrong on a given equation. So you can use this to be able to accelerate inverse problems, but you can't generally just say, I'm going to train one neural network and then I'm going to hand you, this library with a pre-trained neural network that will speed up all of your problems. That generally isn't the case with this kind of method, but people are looking into this kind of idea. It is a very interesting idea, and there's some ways where we think that we can improve it. And so if you want to do research on this, we'd be happy to collaborate with you. We have some ideas.
Yeah. This is an interesting one. Is there something like universal agent-based neural networks where, where you're learning the actions of agents and strategies and stuff like that instead of differential equations?
Yeah, so we put out this paper, generalized physics-informed learning or language-wide. So yeah, so this is kind of what happened with that first differentiable programming paper. People might remember. We ended up doing it to this conference on physics-informed learning, and really showcased how what we're doing with this whole ecosystem is allowing you to embed neural networks in general and inside of general codes, right? So what I've shown here is all these ways that it mixes with the differential equation library and scientific machine learning tools. But there's a lot of other cases here. So for example, the Yao.jl library is also differentiable with the same tools and utilizes actually some components from the scientific machine learning ecosystem, like our exponential utilities.jl that I mentioned really early on. All those things are, we have differentiable portions of them. And so you can differentiate through and do quantum machine learning on Yao.jl. So as long as you can calculate some kind of derivative, you can utilize neural networks in any of these components. And we're trying to showcase that we can do this in very different forms. Now, a general agent-based model, like something like agents.jl, right? So agents.jl is a very great library. It's very fast and it's much more efficient than what you'd find in like, NetLogo or something like Python, but it doesn't have the tools to be able to be differentiable, because in general, agent-based models are not differentiable. There are some things that we're working on to be able to, you can describe the probability flows of agent-based models in certain ways by a differential equation, and then be able to use that differential equation to be able to get fast adjoints. This is still an ongoing project, but this is actually a bit of what we're doing with catalyst.jl. So for example, you can define these models where, this is an ODE version. So you can define models that have, I'm not quite sure where that best example for it is, but in the README we showcase this example that here is actually a Gillespie model. So it's a model where there's only discrete changes, plus ones and plus zero or minus ones. So it's all doing discrete steps, and you can have this is for a continuous time Markov chain, and so these continuous time Markov chains can be simulated directly utilizing this catalyst.jl and our diffuse jump tools, which will have a lot more materials out in the future. And with catalyst.jl, you can use this to transform it then into SDEs, and you can transform it into ODEs. You can transform into all these different other equations that give you differentiable forms. So you can use that to be able to fit it really fast. This is one of the things that we're still building out. So if you want to be part of this project and you're really interested in it, just join us. We're just happy to collaborate.
Have you ever precompiled differential equations with package compiler?
I have not. The reason why I haven't is because I know that we're doing some weird stuff with requires right now. Right. I think that everything that we need to make this work well should be in Julia 1.6. And so there's someone that we have with the Julia lab that's going to be working on DevOps, or who is building all of our DevOps tools right now. We're going to be really looking into how we can precompile this. In fact, what one of the goals we want to get to is we want to have a precompiled version of that library, so that way we can have it be sent as a black box solver to diffie for better use from Python, and then also So not just better use from Python, but also better use from R as well, and also make it so that way it automatically installs and it can interface with JAX and PyTorch, so that way you can utilize this inside of those libraries as well. So we were seeing that this is something that can be in high impact, because there's different packages like climate models and stuff that are now starting to rely on our tools from Python. So we are going to be working on our compilation for that kind of use case.
Okay. Does Phoenix.jl compose with diffq flux?
Not right now. There is someone who there was a code that was put into the Slack that I saved into the issues that shows how to do integration with Zygote. So I do want to talk with Ivan and see if we can get this from take this from something that's a prototype and make it just a part of the standard library. So that way, if you use Phoenix.jl or Phoenix.jl, it'll automatically be differentiable, because that'll be a really nice thing. I really want to make sure that you can utilize finite elements the same way that you could utilize something like diffq operators. I think that one of the things that should be mostly differentiable is JUA-FEM, the last time I checked. It is differentiable in some aspects. I think that reverse diff and forward diff work through it. So it's in some ways, this is a differentiable finite element toolbox, more like DL2. But I think that one of the areas that we're going to be building out in the near future is just more differentiable finite elements. It seems like a very high impact area.
Right. And just to verify, the roadmap for the SciML org is online, right, on SciML.ai?
Yep, SciML.ai. If you go to our roadmap, you'll see a lot of the things that we've done in the past, and we declare a lot of things that we want to make, what we want to do. And essentially, one of the big points here is that we want everything to be compatible with automatic differentiation. So you can just plug all these tools together and just say, I have finite elements with exponential matrix vector products and all these things together. And then we want that to be, that full algorithm, a full climate model. We want you just to be able to say zygote.gradient and have that work. So are we there yet? In some aspects we are, right? So a lot of this talk has us just using, solve directly and things will just work. But there are some areas where we still need to improve. So
right. Does automatic differentiation work with CVOD, the BDF method in CVOD specifically?
Yeah, so we can actually, let me see if I still have this live here. Yeah, it works with CVOD BDF.
All right, great.
So the loss function right now, I guess, is pointing to a problem that is from the volt. Yeah, so it's pointing to the wrong problem. So, but yeah, it does work with the CVOD BDF, because when we define our adjoints, it can utilize actually any black box solver. Right. So let me actually point out what's there, though. A little detail. Oh, oops. Let me get my screen back, sorry. So one little detail to make note of for that is that, let's see, on diffqflux.saml.ai, we go to choices of adjoints. So these optimized and discretized methods that are described here all are able to be, are all compatible with black box solvers. And so the C++ methods, the Fortran methods, you can even call SciPy or MATLAB if you want as the ODE solver, and it'll work with those. These discretized and optimized ones, the ones that we mentioned that could be more stable, these do require a pure Julia method to be able to work. So not all of the adjoints will work with the CVOD BDF, but the main one, the default one, interpolating adjoint will. Yeah.
All right. Okay. So would you mind giving a reference for the automatic stiffness detection? I think just to answer the gentleman's question from Alvin.
Yeah. We actually need to write some of that down. I think that we have some of that in our dev materials. The main thing that I would point to is there's a paper in 1977 by Champagne, who derived some estimators that were never really used, but those are the ones that we dug up for that.
All right, that's great.
Yeah, it's probably much easier to do in the chat. Yeah. Yeah,
I just did that in the chat. Let me see. How does the unknown function approximator deal with arbitrary perturbations in the real world? Example, a super spreader who shows up in the future and spreads it to far more people than the initial data suggested.
Yeah, so what you have to do is you just have to make sure that your model accounts for that. So a SDR model like we showed here is not a good one for superspreader dynamics. Instead, what you need to do is you need to have regional stratification, and then you need to have, on your regional stratification, you have to have network dynamics. And so you want to build a differentiable network dynamics model that then is able to account for these superspreader events. In fact, ODEs in general do not do as well for superspreader types of things. And so I definitely recommend utilizing something like catalyst.jl and its continuous time Markov chains for that kind of model. Yeah, it's really about just matching the right model to the right problem.
That's right. That is right. So there's a question about galactic optim versus jump, but I guess that's not relevant to this workshop. So I would encourage asking that on Discord.
So galactic optim.jl, it's more about utilizing code. So you give it a code, and then it'll be able to work with all the different optimization libraries. In general, jump.jl has been a very good optimization interface for linear optimization, quadratic optimization, mixed integer programming, all these kinds of things. But where it has not done as well before is in the nonlinear space. And so we've really just been taking it to, just basically do like a nonlinear version of jump and try to do it work so that way it works on equations. We utilize modeling toolkit to be able to look at your equations, generate symbolic forms, and send those to the solvers when they ask for them, and all these kinds of nice tricks. So that way you can just use normal Julia code with very good nonlinear optimization packages. So yeah, we're only looking at nonlinear here, whereas jump really takes the crown for anything that's not purely nonlinear.
Nice. And okay, are you going to link the slides anywhere, or you're going to?
Yeah, I'll be putting the slides up.
Do you know where? I guess attendees want to know.
Might as well put them onto SciML tutorials.
All right, so you can find them on SciML.ai, right?
Yeah.
All right, great. Yeah, I think this is the last question because I don't think we'll have time to get to everything. So, you recently, sorry. What's the comparison between the SDE functionality in DiffyQ versus the Torch SDE library that was released recently?
Yeah, so the main thing is that, so when you have very small differential equations, right, Torch does not do very well at optimizing the scalar optimizations, right? So when you're writing down these chemical combustion models and you're writing down these ecological models, when you do a lot of these scalar operations, we see that the Torch libraries do not do very well there. And what I would point to for that is SciML benchmarks.jl. So I would say take a look at this. This is what you can, just run it on your own computer and see that when you try to utilize Torch script with Torch DiffyQ, it can take 48 seconds to do just a forward pass, or it's 1.6 milliseconds, right? And when we're talking about 48 seconds, right, I was demonstrating live here that we're solving neural ODEs in 3 to 4 seconds. So, even though the gradient is actually the more relevant thing to time, there's a pretty large difference here. And this really just comes down to the fact that once you start to do all these indexing operations, then you are missing a lot of the optimizations that a lot of machine learning libraries can handle. Even Julia's Zygote does not handle these indexing operations well. And so we utilize other optimization tools like modeling toolkit and reverse diff, things made for scientific computing libraries to be able to handle these cases very well. And so definitely if you're doing some kind of scientific modeling, which generally has these, sparse forms and has these, these network equations, these things do very, very well with the Julia libraries. There's less of an advantage with the Julia libraries if you have a very, regular equation. So a regular equation is something like a neural network, which is mostly just doing matrix multiplications. In that case, we have seen that for small matrix multiplications, with the example that I'm demonstrating here, took like 300 seconds or so in which Torch script, Torch DiffyQ, and we can get it down to 3 or 4 seconds because we're utilizing a lot of things that are very well optimized on CPUs. And then when we go to GPUs, we can utilize similar GPU libraries. And so where we're then as you asymptote to larger and larger and larger and larger differential equations, then Torch DiffyQ's effectiveness will start to asymptote to become closer closer to the differential equation library. There's still a few things that we're doing extra. So we're utilizing some extra time stepping techniques and other different methods to be able to get more efficiency. And so that's where we can still see, for example, that's really where you get the difference from JAX, which is able to optimize this case really well. So its compiler does fine on the problem that was given, this Lorenz equation, but this difference is just purely in the time stepping domain. So that's just, so efficiency-wise, as you asymptote to like a very, very large neural ODE, you'll see this timing difference kind of fall away, except for maybe a 2x. And then, they're both able to utilize GPUs, but GPUs at this point, everyone's calling the same cuPLOS and everything, but it doesn't, the compiler difference on GPUs is not very relevant. It really just comes down to number of function evaluations. And so really where we then have an advantage is that we have a lot more different methods that handle a lot of different cases to do it in very few function evaluations. So for example, the TorchStiffEq and TorchSDE libraries only have methods like that are for non-stiff equations like DP5. So for example, this equation right here that I demonstrated, if you try to solve Rober's equation with that, you'll just straight up get a failure. This is one of the big example equations that just won't be solved with a non-stiff method. So there's a much larger class of methods that we can handle, or problems that we can handle, because we have very optimized methods for many of these different cases. Now specifically on stochastic differential equations, their stochastic differential equation library has only a subset of the methods that are for so it has a subset of the methods for strong high order on diagonal equations. So if you have one of these very non-stiff diagonal equations, and it's so if you have a very non-stiff equation where it's a diagonal stochastic differential equation, and it is very regular, so you're using very large matrices, matrix vector multiplications to get around this indexing issue, then in that case, you could expect it to be very similar in timing. Whereas what they do add, what TorchSDE adds to that case is that if you have a very large stochastic differential equation like that, they do have a way of doing the backsolve adjoint on specifically only SDEs that will reduce the memory usage. So they do have an advantage in this very large neural SDE case where you have very regular equations and where you're hitting a memory limit. In most of these other cases, we have an advantage, and we'll be putting out a lot more of these benchmarks in the near future. We're just finalizing them because we like to show benchmarks in a way that shows both error and time at the same time. But as you could imagine, when you do that on stochastic differential equations, it takes quite a while to be able to optimize and really be able to create these work precision diagrams for stochastic differential equations. But I mean, on the smaller equations, you can just, if you just run the equation, you'll see a pretty order of magnitude difference on the smaller ones. Yeah. So for that difference, we are working on getting that version of a backsolve into this our adjoints. So the backsolve that we have right now just has to save the noise as it goes forward. There's a way to be able to not save the noise as you go forward. Right now, they do have that memory advantage in that asymptotically large case.
Right.
That might have been way too much information, but yeah.
I'm sure everybody loves it. I think at this point we should probably end the workshop. I mean, we've gone half an hour over, and yeah, this seems like a good time to stop. Well, thanks, Chris. Thanks for such a great workshop. Everybody has very good things to say about it. And on the chat, I'm just scrolling through the chat. And on that note, thanks everybody for attending.
And thank you guys, and contribute in the different ways that I mentioned, right? So start the libraries, answer questions, write blogs. These are the ways that we like to grow the community. And if you do want to do research in the SciML ecosystem, we have tons and tons of opportunities. So just get in touch with us. And there's so many things that we have just waiting to be done. I think that there's a few things here that I kind of even mentioned just verbally, like, oh yeah, we work with Turing, and we can put neural networks inside the differential equations. What is a Bayesian neural ODE? Well, you could do it, right? So let's talk about it. So yeah, so there's so many just waiting opportunities just to be done, and it'll be fun. So just find me at JuliaCon. I mean, you can't find me in person to talk to, but you can type it out, and I'll chat with you guys, and let's just do a lot of really fun scientific machine learning.
All right, thanks, Chris. Thanks, everybody. Take care. Enjoy the rest of JuliaCon.